Okay, welcome everyone for this wonderful space science seminar. Today we are very happy to have Arnab from SINP, and he's going to tell us about brachyzones.
Thank you. Thanks a lot. Thanks a lot, everyone. It's been a while. I think last time I was here, the world, before COVID, yes, the world was fluctuating around a different saddle. Because in many ways, I think the saddle is slightly different now. In fact, I was probably supposed to come at some point, and then pandemic struck. And anyway, so I'm very happy to be here after a while. And what I will try to tell you today about is something I'm personally quite confused about. And at the beginning, I thought that this is an absolutely childish thing to try, and nothing will come out of it. But here I am after 2 years, still confused about it. But there is something interesting which this seems to be giving us. And I'm sure you have heard of some version of it, because both I think I and Chetan have given multiple talks on this topic. And essentially, what I'll say will be, well, the base of it is essentially rooted in various works we did with Chetan and my student Shumon, who is now in South Africa, enjoying lions and so on, as I heard. And also other people joined in later on. So it sort of grew. But I should say that, I'm also in a bit of something I have also mentioned somewhere. The situation that I find myself in is like, the food is the food is too bad and there is too little of it. So it's a bit of a conundrum. But with all that, let me start. Well, no, not food, but yes. Neither too little nor too bad. Yes, I agree.
But
too much.
The conundrum is that it's so bad that you still have to eat.
No. Yes.
You have clearly never faced this conundrum.
No, I think the conundrum is this old joke, right? That the two ladies sitting in a restaurant, one complains that the food is so bad, the other one says yes, and there is so little of it. That's so much there. So that's not conundrum, it's the irony, I guess. Okay. So with that, let me begin, and I would really appreciate feedbacks and so on and so forth, because I think there are some things which I'm quite certain that, well, anyway, I'll mention things anyway. So we'll try to talk about today mostly about various things that is supposed to appear in this work, which is in the to appear stage for at least 6 months now. But anyway, so I don't know about you, but I kind of get excited with numbers. So I will begin with this picture, which of course I don't have to in front of this audience. But what I really like is this the confidence at which we can now say that we have detected black holes. And of course, this is the Event Horizon Telescope. That's not the sensitivity that I'm talking about here. This is more of the sensitivity of the LIGO. And with gravitational lensing, etc., you can go up a few orders of magnitude, like 3 or 4, I hear. Not that I know. But of course, the thing that we really want to understand is what's happening at the quantum scale and so on, which is happening which is supposed to happen at 10 to the minus 35 meter, which is still 10 orders of magnitude to go. That's L-Planck, yes, exactly. And that's very unlikely to happen perhaps in our lifetime. So it's kind of still a very, very far-fetched hope in some sense, in some realistic sense, to see some signals of it. But once you see
sensitivity 10 to the minus 24 meters is the sensitivity of what?
That's the LIGO. That's the metric perturbation candidate. Which is just this number is remarkably impressive. I didn't really realize that it's at that level. I knew about LIGO, of course, but the number, that's why I said that numbers sometimes help. It's amazing that.
Now we sometimes translate length scales to mass scales.
Yes.
And this would be much higher than the LHC mass scale.
That's true.
But it's just a different kind of thing.
That's it. We are not doing particle physics collider experiments at that scale. So of course, this picture is very thought-provoking, I think, because it automatically says, it automatically raises.
Sorry, but just to continue,
yes.
Why aren't fluctuations of everything else, like the little atoms and so on,
yes,
very important at this?
So now we go into LIGO.
Yeah, that I don't know. That's a good question.
Key question in LIGO.
So I think
the mirrors are fluctuating.
Yes.
They integrate over. Okay,
They
it's miraculous. right?
apparently they can model all the noises, and now with AI, etc. I don't know.
But what about quantum fluctuations of individual atoms? And they know them well enough to
I think they can systematic noises of that sort they can model out.
but you can remove it because
Yes. Yes.
So I think one thing is that this is a little, I mean, it's great, but it's also that I think you're sensitive to this probably if you can integrate over enough time to
I
fit
guess
a
so.
chirp
Yes,
pattern or
yes.
something.
You have to.
You know,
yeah,
you
that's
use all that, your various templates and then.
correct.
You know,
I mean, I don't do any of those things. but
Neither do I, but I mean, towards what Shiraz is saying.
Yes.
You know, all that goes into saying.
Yeah, it's completely different frequency. Like this length scale is the amplitude, but the frequency is not of these frequencies.
That's correct.
I think that must be it.
Yeah. So when you integrate over that, you know, then and that also you can distinguish between, you put in a little.
Yeah,
Yes.
the frequency is 10 to the power minus 3 seconds, right?
That's right.
Of the wave. So you're interested in this amplitude, but at a frequency of 10,
That's right.
at a very human frequency.
That's right.
And
That's right.
somehow that's
Somehow they can do this.
Yes.
That's quite amazing. I mean, in fact.
But still, of course, it doesn't take away.
But yes, the
but it
challenge.
makes it more believable.
Yes. So, of course, there are extremely interesting questions associated to this. For example, one of it is, did we really detect a black hole or something which is extremely compact? Which I think is an observationally open question. Even the line people say that that's a question which is far from being settled, but let's just settle for the black hole because that's the way best understood in some sense.
Say again, what was the open question? Sorry.
So the point is that if you ask the LIGO people that to what confidence we really claim that we have seen a black hole and nothing like an extremely compact object. To that, the answer, I think that the technical answer is that you can make a multiple moments expansion, and up to second moment, you are reasonably sure that this is a black hole. But if you go up higher, the sensitivity is not enough to say whether it's a black hole or let's say some hairy object or some star. Now you can of course ask, how did that star form? How can it be so small and so on and so forth? These are all theoretical questions, which, as any theoretical challenges have, you have bypasses of it also.
But also the ring down, right?
Yes.
I mean, the final stage of the
That's right.
spiral, that ring down, etc., that really fits the quasi-normal.
That does, but that is
But you
correct.
say that's still not. Huh?
But it may be, if you have a very long throat, like a very approximately ringless structure, that could be enough to fit the ring down there. There could still be some small structures around that scale which you are not seeing.
Suppose you modify something just epsilon away from the horizon. Then by causality, that will show up only very late.
Exactly.
So you can always modify near enough to the horizon and not see it for a very long time.
Exactly. In fact, essentially what you just said is what exactly I'm going to do, as you probably know.
So we just gave this talk, right, where he was distinguishing neutron star mergers with black hole from black hole mergers and so on. I know was there in the talk. Right. I saw. They just we just because this is the kind of question you consider whether how to distinguish these things. And he had some elaborate way of that.
Right.
I don't know whether it was based on that saying what he was saying, but
Well, I mean, at this point, I think it depends on what kind of star you're thinking of, because I mean, there are several things, right? I mean, neutron stars are not believed to be extremely compact anyway. So for them to be distinguishable from black holes is not very difficult, I would imagine. But you could still think about some crazy stuff, exotic matters that forms extremely compact objects and so on and so forth. Well, then how do we see that? And this length scale although seems kind of hopeless, but I just want to say that it also raises these various possibilities about the quantum structures of these ultra compact objects or these black holes and so on. And just I don't like to put people in boxes, but here I am exactly doing that. Unfortunately, but there are several thoughts, of course, which are very, very influential in the field to understand quantum nature of black hole. And I'll just mention nothing to do with history really, but very recent, classification of thoughts that people have had. One is, of course, the school of thought is that, well, there is a black hole and the horizon is perfect, it's smooth, no problem whatsoever in there. And if you want to understand quantum properties of this, one way of doing it is to resort or is to understand the Euclidean path integral. And if you do it properly, then you learn a lot of, in fact, ultraviolet physics lessons out of it, which is a bit maybe counterintuitive. And in fact, it's a generally a great question to ask. How much UV physics can we get out of just doing some Euclidean continuation of Lorentzian theory and so on? But nonetheless, there's a large literature now which has very many explicit computations of, let's say, fine-grained entropies like Brennings and so on. And essentially, primarily based on, perhaps it's fair to say that the Gibbon-Stocking analysis and its further generalizations, modifications, and improvements. And this essentially presumes that the horizon is a perfectly smooth and nice place. This is a very influential, I think, idea. Yes.
Sorry to interrupt.
Yeah, no.
I wanted to say this in the previous slide, but just to say it here, probably the most likely way to see quantum properties might be for small enough black holes, if they do exist. You see Hawking temperature, Hawking course, right? I mean, then we would declare that it's quantum.
Of course,
Okay,
yes.
all right.
Yeah. But that, I guess, I mean, with CMB, etc.
You need a lot of conspiracies. We don't know if it can be done.
We have to be very lucky in some sense.
Lucky.
Yes.
Sorry, I just one.
Yeah.
About you modify a black hole very near the horizon.
Mhm.
Now, the thing that you modify has to be able to stay there.
Yeah,
That's
it's
right.
almost impossible. It's
It's
going to fall in.
So, okay, neutrons start 2 or 3 times the size can manage.
Yes.
But something nearer and nearer sounds less and less.
Very hard.
Yes.
Very hard.
That's
Actually, I want to say. So,
That's right.
yeah.
So I'm going to comment on that. This is not really something I work on, but this is where at least the second community, which I call fuzzball community, have been spending a lot of time. And one of the main goals there is to essentially come up with situations where you can support the structure at the scale of horizon without collapsing.
But the scale of horizon, twice the horizon?
Actually,
Neutron star scale of horizon, right? Or is
well-
maybe the Chandrasekhar limit of the neutron star, sort of like a.
yes, no, it's
Okay,
much
okay,
much
okay,
close, much close. So that's the challenge, right? Neutron star, you can easily
What would the ratio be of neutron stars?
I think there they have parameters which you can tune arbitrarily.
No, but just in the real world.
Oh, the real world.
Neutron star.
You mean the
Yes,
neutron
yes,
star?
yes, yes.
That I don't remember. But
Is it like 1,000?
no. I think it's order 10.
10. Okay, so that's scale of black hole. Okay,
No, I think they want parameter. They want
something
parametric.
near to that.
Yes, you can actually do that. And the claim is that there's a paper by Warner and Gary Gibbons to say that essentially you can do it by using extra dimensions and fluxes and so on. Somehow that can evade the no-hair theorems, and you can form structures if you have enough fluxes in the compact directions and
So
so
I
on.
just understand that statement. So you can form structures that you outside it's essentially indistinguishable from the horizon
That's
until you
right.
get to some epsilon.
Exactly.
That's really
That's really the claim. That's really the non-trivial claim. And the further claim is that it's not just a statement. There are solutions which do that.
But in the real world,
Well, these are
if you had extra gauge fields and higher form bleed, you will okay, fine. But in the real world,
You mean
what's there? Just
you mean-
electromagnetism? There's there.
yeah, no. By real world, you don't mean 10 dimensions and so on.
No. I meant 4 dimensions.
Yes, then I don't know. Then there is one way to do it, very effective sense, which is that you conjure up exotic matter which has let's say wrong kinetic energy. Then you can do that. That's obvious.
Then
But the point is that the claim is that if you take these higher dimensional theories, sometimes reduce them, they can look like these theories.
So how is this obvious?
Which one is the the negative kinetic energy will sort of simulate repulsive force. Otherwise, you can't stop gravity from collapsing.
Then why would it just go away?
No, you can balance them, right? I mean, the gravity is that's the balancing part. It's exactly like how neutron star is stable.
Even the 10-dimensional claim sounds surprising.
This is not a claim I understand at a technical level, but this is there.
we've taken sorry, Lie-Brain like objects or something.
Yes.
Is what I'm thinking,
But why don't they fall in?
maybe for G.
No, there are certain cycles which don't collapse. There are certain topological reasons, I think, which there are certain cycles and so on that in the higher dimension.
This I'd like to understand. I thought somehow intuitively this would be very hard.
No, apparently, yes. This is something I don't understand at a technical level. And I will support you.
Black holes are finite size, right?
Yes, yes. Yes, but BPS. Yeah. Finite size BPS. That's right. Good. So that's the other school of thought, which says that the horizon scale, you have structure, you go there, you hit something.
Sorry, this is what one means by fuzzball, right? In conventionally.
Yes, yes, exactly. And this is, I mean, yeah.
By the way, I want to say you've left out one community, if I may say, which used to have a presence in TFR, doesn't anymore, which is the community which believes that cosmic censorship can be violated. And therefore collapse can give rise to naked singularity.
Okay.
This community has a non-empty set.
So that's why I said that this is not historically accurate. This is just.
So that's fine. I don't believe in that claim, but anyway.
So
Sandeep saying it's not history.
Anyway, I mean, of course, there is. So this slide is really to say that there are all these extremely powerful ideas, none of which I know very well. But anyway, and also, of course, the third, I would say, mirror operator community. I don't know if it's a term which will offend them or not. But there is other ways of thinking about smoothness of the horizon, which is slightly non-Copenhagen quantum mechanics. But this I know the least about. The other two, well, I have some infinitesimal knowledge, I guess. That's that. So I mean, given that, you see, ignorance sometimes can be bliss, and I can do whatever I want in some form. So well, of course, I mean, I think this is true that we don't really know what the quantum description of black holes are going to be exactly going to look like. So we'll take that advantage, and the question that you can pose already, that, well, what is our chances of observing any such thing? I mean, it's likely historically you could have posed that question for atoms also. We did not really observe atoms by having a resolution at the atomic scale. We observed Brownian motion. So there is mesoscopic physics, and in fact, there's a very nice, I would say, article by this gentleman. They're mostly actually fuzzball motivated. They want to understand whether there are signatures of fuzzball in experiments that you can write down and that you can pin down, you can go and test, and so on. But the point is, of course, that you have to come up with certain mesoscopic observables. Otherwise, who's going to observe this 10 to the minus 35 meter scale resolution of anything? So it is possible, and that's kind of the hope. And what I will do today is what I will call a fuzzball-inspired effective geometric picture. None of these words are probably very precise, but anyway, you'll see what I mean. And this is something that was considered by Cook a long time back, and also by Israel and Mukherjee in a very nice paper about a decade after. So what you do is very, very simple. What you do is very, very simple, but ad hoc. You take a black hole, and you place a surface slightly outside the black hole. In fact, let's say you have the freedom of placing this surface outside the black hole, just outside the black hole, or anywhere else in the geometry. And because now we like ADS-CFT, we have that power, I'll just choose to put it in a ADS box. So the ingredient here is, first of all, this, I want to emphasize this, this is completely non-dynamical and ad hoc. I cannot support I cannot give you a mechanism that places this object near the horizon or anywhere else for that matter in geometry, and why does it not fall and so on. But this is just something I'm going to show.
Dirichlet wall means induced metric on that surface is specified?
You can do that, yes, but what I will do is I will put in certain fields here, which will have Dirichlet boundary condition on that surface.
So non-gravitational.
Non-gravitational.
But for the metric, you're specifying the induced metric or something else on that? Suppose I wanted to also look at fluctuations of the gravitons.
Then I guess.
Just to understand what it means.
Then I guess you have to impose, fix the
induced metric.
Yes.
So it's not enough just to posit that you have this non-dynamical whatever surface near the horizon.
Mm-hmm.
You also, and then asymptotic to flat space or ADS, you need this additional break. I need two surfaces.
No. Sorry. This is probably what I meant by these two lines here is that you can put them anywhere you want. At a time, I just have one of them. Forget about this dotted circle.
Oh, okay. So you could just have asymptotic ADS,
Yes,
but instead of a black hole, when you go close enough, you have your boundary.
exactly. Exactly. And it is really something very, at some level, anyway, let me, that's the picture. Of course, this picture,
Please excuse me. And then at that non-dynamical boundary, you would put Dirichlet boundary conditions.
yes.
So that means there's no, I mean, we expect the metric to sort of fluctuate as things fall into the black hole.
Right.
And this is just different.
This is just different.
So
Yes.
this is really, I think, true of brick wall movement.
This is really top spring.
Near the horizon.
Exactly. This is exactly.
So you will be putting this boundary wall close to the horizon? Or
That is the place where it will have the most interesting effects. But you could put it anywhere else. It will have slightly less interesting.
And so when you send something towards this thing, it'll reflect.
It will reflect back.
But it'll take a long time to come up.
Yes, that is my freedom of placing the wall, where I place the wall, precisely.
Yeah.
Precisely.
not reflecting with fine.
No, this is reflecting. This is perfectly reflecting.
Less flux to the right.
No.
No,
No. It
this is wall,
Oh.
literal wall,
Yeah.
literal wall. You go and hit and you come back. So in that sense, it's sort of fuzzball inspired,
Okay.
but I don't want to push this, well, anyway, for other reasons. Okay. So that's really the picture, and it actually probably raises more questions about what the validity of this picture might be, but nonetheless, let me go ahead with it. So the question, in some sense, you can form it in the following way. So are there boundary conditions that can result in a very non-trivial dynamics in an ordinary manner? That's what I'm going to do, because I just change the boundary condition at the horizon scale, and there will be some fields propagating in it. And I'll just say that, okay, you have no choice but to have the Dirichlet boundary condition. You may say that's a wrong choice, but fine. The question you can ask is whether by tuning boundary conditions, I can generate interesting physics. In some sense, the answer is already known. But for example, one of the things that you could ask is whether we can understand thermalization, decoherence, maximal chaos, quantum chaos, whatnot. And the question that Thuk really asked was, how do we understand area law entropy from such a system? And in some sense, he answered that, which also, of course, raises more questions.
So sorry, suppose I'm
Yes.
just doing classical propagation of a minimally coupled scale of field.
Yes, yes.
So then is there a theorem that is that some range of space-time I can make for which, if say the question is I hit the boundary,
Mhm.
something goes in, and I want to be able to claim that the response in some region of space-time will be identical to that of a black hole, just by causality. Is that
Yes. I mean, classically, I think yes. Classically, I think
So once we put the Brook wall at epsilon, I just look at the light cone of that epsilon,
precisely.
and then anything outside outside that light cone cannot know that there was a brick wall there.
Exactly.
And so the evolution is identical to a black hole in that region.
Exactly.
Okay.
Exactly.
So quasi-normal, many things will be
Many things
basically
will come up. Many things will come up, and that's I guess it's a technical question. How do I
Sir,
see it?
can you draw the Penrose diagram with this?
Penrose diagram is going to be tricky because I don't have two sides, but
This used to be also. the
I can
kind of-
draw, if you want, this thing.
So you can draw the Penrose diagram of a black hole and then put your brick wall.
Yeah, of
It is
course.
the dotted.
If you
Just
want,
hugging the horizon.
yes.
Yeah.
That time delay, because it's almost in arbitrary.
Ah.
It's almost infinite, but it'll get out.
It will reach eventually log, right? Some log.
Yeah,
Log of it. T will be log of it.
exactly.
So what
You're
you
cutting it off like
That's right.
So what is the reflection? How will the reflection look like?
Well, you send something here,
Yeah.
from here, let's say,
Mhm.
it goes in, and then it reflects back. That's the
like-
boundary condition.
But it can't, it has to go in the light
It,
field.
it reflects
Yes.
that, but actually it's
It
hugging.
hugs,
yeah.
So it takes forever, but finally
Yes,
does
yes,
come.
It goes within the light.
Yes. It will take longer and longer the closer you take.
So your theorem is in that.
Within that match. So you make epsilon small, it's almost all of the exterior of the black hole. Right? This is why many things are guaranteed to, right?
Yes, I agree. I agree, completely agree.
Yeah.
And in some sense, that's what Tuf did, and I guess, I mean, anyway.
In the old days, when Kipthon and so on, they developed the membrane paradigm.
Yes.
They had a similar thing.
They had a similar.
As far as the outside is concerned, they want you to dumb down GR, right?
In
So
some
astrophysicists could use their intuition. No, I'm sorry, this is actually I mean, this was actually the stated motivation. They wanted to dumb it down so someone who doesn't want to bother about Einstein, just say this is some normal object and I can do most of this. And you can do quantum.
Yes, I mean, in that sense, I think.
What you're doing is very interesting. I'm just saying.
Yeah. So this is just, I guess, it's another way of looking at it, but slightly different properties, let's say. And
That's the wormhole,
Yeah.
right?
so exactly, the wormholes cannot exist. Not in a way that I can
You won't get fluid gravity out of such a black hole
probably know.
because the black hole itself is not allowed to vibrate around. Right?
Yes.
You without them because.
Oh, but you must somehow. Yeah.
I mean, if you have quasi-normal modes,
Yeah.
So-
you must.
but it may be not quite due to symmetries. I don't know how.
So quasi-normal mode is actually something I want to talk about because at some level it looks like, well, if you impose Dirichlet boundary condition, this is like just a standard particle in a box or quantum field theory in a box. How do you get quasi-normal modes out of that? That's the part which is not immediately obvious.
But it must come. It must come, right?
It
Because
will
of
come.
theorem.
It will come in a way. Yes.
Yeah. So even fluid gravity must somehow come.
Yeah.
So I think
Long
But not for large fluctuations.
no, not
large-
for arbitrarily long time.
This is like a linearized kind of thing.
Yes.
No, not just. It's also like the amplitude. Fluid gravity moves the position of the horizon significantly.
Yes. That cannot happen.
That can't happen.
That can't happen.
But then they must, I mean, usually, Shiraz, of course, you know this better than me, given the quasi-normal modes and symmetries and so on, hydrodynamics follow.
Yeah.
Right?
So when you try to make it non-linear. But I'm saying this non-linearity is going to be a problem. Because they fixed where the horizon is
Yes.
right from the beginning.
Yes.
Whereas in a dynamical space-time, it chooses the horizon.
That's right.
You could have always said that there exists this wall at a proper time or proper.
No, I can do that. See, I mean, so what Shiraj is saying, if I had let's say a theory whose solution is this, that there's a black hole geometry and slightly outside of it there's a wall, I could take that theory, I could fluctuate it. And that would be my entire fluctuations. I don't have such a thing.
Let me say it again. If I give you a space-time,
Yes.
and I ask, can I set a particular, is there any surface on which I got a particular inducement? The answer is no, right?
Yes.
Because the degrees of freedom you have to move with for a surface is 1,
Yes.
whereas the induced metric is d square,
Yes.
d square by 2. Right? So I can give you the metric that comes out of fluid gravity, and I ask you, is there any surface on which your boundary conditions will be obeyed? The answer will be no.
That's right.
So,
That's right. Yeah. So that's exactly. So that something like that, I still don't know how to do. But
But at linearized level, because you have a long time scale, they'll be ring down. No?
yeah,
there will be ring down.
I think everything amplitude that doesn't require large amplitude. Anything requiring large amplitude will not.
Yes. That is true. That is true.
Wouldn't that already, I mean, this is just classical analysis will tell you that kind of model.
Yeah, I mean, field
Yeah.
theory does have fluid
Yes.
dynamics.
Yes. But yeah, I mean that you want to see, for example, in, let's say even a first quantized theory, how that works and so on. Right. So what I'm going to do is not just a lifetime calculation, although that already tells you a lot about how it should work. In other words, I mean, you can again, I mean, it's just rephrasing the same statement that you could ask that there are certain physics I expect, and can I do something to the boundary condition so that it gives me that physics? Now, it may not be that this particular boundary condition is what will give you the entire physics that you want. That's quite likely. So anyway, so there are several examples.
How did the
like-
fluid dynamics?
Sorry, yes.
How did the fluid dynamics make this causality?
You see, because what you're doing is specifying a background spacetime. And say physics in that background spacetime will be more or less identical to physics in the background time. But in fluid dynamics, the spacetime itself is moving.
Yeah, but unless you get the space-time somewhere within that time, well, I mean, isn't there some causality theorem which says that your fluctuations will only be inside
Interesting.
that causal line?
Interesting.
Unless you get it somewhere within that causal line.
But the thing is that the dynamical spacetime may move so much. Let's take the real thing. The dynamical spacetime may move, the horizon may move so much that things that look like it's near the horizon could go well outside of it. So then you would see that much earlier. But you're saying that's impossible. I don't know. It's a good question. It's a good question.
I feel somehow that at least that causal diamond that you were drawing will.
Food, I don't know.
Affected, but okay.
Could be.
This is probably here.
It's a good question. I don't know.
Could be.
You know, but if the horizon starts moving around, right, as a response to stuff falling, that's what happens in a real horizon,
Yes.
right?
Yes.
Then that would begin to deviate from yours.
Yes, of course.
You know, I
But
think
then,
that's the
unless
point,
one has
right?
a mechanism of adjusting the boundary condition also according, which is why I say that I need a theory whose solution is this. Then I can do everything at least within that consistency.
But I mean, without that, as you're saying, you just posit that, you know, you have.
Exactly.
And now if it starts moving, unless you say as the horizon moves, I always
also
keep
moves.
track of, you know, that's a sort of different, maybe that's what you want to say,
You
I don't
could
know.
probably do that there is a fluctuation of the horizon and you accordingly adjust your boundary
Adjust.
condition.
Yeah.
That you could, but that
Then
you have to again do by hand.
Huh.
But that's what I was saying that whatever, even if you don't do that, the whatever effect is, it's very late times.
It's very
It's just going to be outside this time.
But late times in which?
Yeah.
In which measure?
I mean, there's a causal diamond that's being drawn, right?
But in that background range.
Yeah.
Yes.
But
As long as I'm not hitting the boundary in that causal diamond, how can the solution change that?
But in falling Eddington Finkelstein, constant V metrics will be.
if, you know, what you're saying sounds to me like the following question. Like the Marcus-Eggers-Stein theorem, which is that if in flat space you couldn't have reached earlier, then you couldn't reach in any process.
Something like that, yeah.
Okay, that's the kind of thing.
Yeah, yeah.
It's not clear to me that rules for these kinds of things. You know, that because as Sandeep said, once you push things in, that pushes the horizon out.
Okay.
And that changes the causal nature in the direction you. I'm not sure.
Okay, okay, no,
Yeah. But I mean, there's something to check, and I don't think it's obvious.
it's not.
Yes.
I mean, small changes near the horizon change times by a lot. They times a lot. So, you know, you can't ignore those small changes. It's okay, anyway.
Yeah.
So exactly. I agree. Good. So yeah, okay. I don't think I need it's
That's why
just to say
one
yes.
last
Yes.
question.
Yeah.
But when you put this cutoff, your calculation, you will just fix the background.
Yeah.
You will consider some minor things.
Exactly. That's the thing I can do neatly.
Because if you started correcting the metric, then you would have to specify this this cutoff surface.
Then I need a mechanism to adjust the cutoff surface.
Right, and you would have to specify it in a different learning period.
Yes. Which I do not yet know exactly how.
But something like inducement.
Something like inducement.
This metric or in there, I mean, that's
That's
a
a common.
or you know, you could ask to put the surface at some fixed upper distance from the horizon. I mean, there are various ways you could do it. Right?
Yeah.
Okay.
I mean, there's one particular.
Along some slides.
Yeah.
Along some particular pre-specific, some angles, you have to choose some angles. Okay.
Not sure what.
Yeah, I understand.
But if you imagine the equations for these obeyed by this surface, then all this is just some convention, right?
All this is just that's true.
Yeah, that's another way to say.
In a coordinate independent way, when you said at a distance epsilon,
Yes.
what exactly?
So this I'm going to really explicitly make reference to the particular coordinate, but of course, given that epsilon, I can always convert it to a proper distance. That
I mean, all I was saying was, I mean, one way to say it is where the surface gravity, that is, you know, the amount of acceleration a rocket
Sure.
needs. Huh?
sure.
And then you can keep it at that as stuff falls in and bounces back.
That's right.
So at least that's some
Yes,
specific.
that's right.
Okay.
Certainly, I mean, you can do it in a coordinate invariant, perfectly invariant. Yes,
Okay.
certainly.
But then it will start differing from the horizon dynamics.
Yes.
Which is
And-
purely ingoing.
Yeah, and in fact, I think one particular reason this sort of back reaction is very interesting is if you want to do a OTOC kind of calculation. There, I think this is very crucial because I don't yet know how to mimic such a calculation in this setup. But yeah, that's anyway. But I don't have any precise things to say yet. Something
But certainly because if for long enough times you graze the horizon,
right.
with this edge.
With this,
As this time longer you come closer to the.
exactly, so exactly,
The longer.
exactly, precisely. And yeah.
Can't you hold these things in place by cosmic strings or something? Like, Ashok has this solution of magnetic dipoles where they're prevented from falling into each other by cosmic strings.
I see.
They are also spherical solutions.
I see. But by attaching strings all the way to
Yeah.
the boundary, could be possible. I have not tried this. I mean, but the joints would somehow form kings, no? Or
I think there are quantum singularities in this.
yes, so that conical singularity is something I don't yet want. Because I mean, this is like hanging something by a rope. At the joint, it will always, it's a triangle joints.
You want the smooth.
Yeah, so smooth, I don't know how to, maybe infinite number of cosmic strings.
So just coming back to Omkar's question. There's this theorem in general relativity by Hawking and Penrose, I think, that if I, sorry, to
Yeah, no.
if I give you the data in some region, then the metric in the future light cone of that region is just completely specified
Yes,
and independent of the data outside that region.
yes.
So I suppose this is the kind of thing one has in mind. So I give you the data here
Yes.
and then on this boundary.
I was just about simple enough. Maybe it's what was the exact thing? I mean, there's clearly a difference in a boundary which has Dirichlet and a horizon which is purely absorbing, right?
Yes.
Because when it you have to put in the back reaction.
That is
but
right,
then
that
there's
is right.
difference, right?
Yeah, but just going back to just plain flat space, no boundary. The theorem there states that if you have I give you the Cauchy data in some region, then it determines the metric inside its light cone. And you can ask, what does that even mean? This light cone, what does it even mean? Because light cone in what? And it's that the light cone, as seen from inside, it's self-consistent. Inside is self-consistent. And it's smoothly joined to the light cone as seen from inside. And the point there is that no matter what you do to the data outside, you'll change the space outside, but not here. This is the notion of causality and generality. So you might wonder whether some such theorem holds.
Yeah, I was thinking that now you're specifying the data on the asymptotic boundary.
Yeah.
Not in a time-like space. But maybe this is the main difference that the asymptotic boundary is this.
Yeah. It feels, you're saying modern it feels. I take your point. Yeah.
HKL, we do HKL, even though it's not an
Yeah.
Sorry.
Good. So, all right, let me go ahead. So, anyway, so this is something I think everybody knows by now. Just a few elementary words about quantum chaos and so on in generative systems, not just black holes. And in fact, these are very known statements. So, of course, if you want to look at the quantum dynamics of any quantum mechanical system, there are several timescales. And the lesson that that has become very clear to people is that there are various timescales at which interesting things happen, interesting qualitatively different things happen in the system. And such timescales are, for example, the dissipation timescale, the scrambling timescale, and the Heisenberg timescale, for example. And then there are observables, that you can measure to essentially get information about these various timescales, like just a simple 2-point function that will give you dissipation. If you want to know about scrambling, then you compute things like out of time ordered correlators, 4-point functions in general, and so on. But if you want to know really Heisenberg time, then you really, in some sense, have to solve the full system. In other words, compute the spectral form factor that essentially scales as exponential of entropy of the system or the number of degrees
What
of
is
freedom.
delta to the -1? What is
Sorry, delta is the minimum gap or the average gap in the spectrum. So yeah, the inverse of the density of states. And yeah, that is something that we all know pretty well. So essentially, this is one of the reasons I find it kind of interesting is because nowadays people can actually simulate quantum systems for very, very long times and actually see these things. Of course, not in systems with many objects, many degrees of freedom, but still somewhat manageable. And this is something that that people also have understood in terms of something called return amplitude in thermophile double states. It's very standard stuff. So if you write down a thermophile double state in this manner, which is all familiar, and then you consider that you evolve this TFD state with a Hamiltonian, which is basically just a linear sum of the two Hamiltonians, H1 and H2, which essentially give you this whose eigenstates are this N1 and N2. And then you want to compute what is the return probability or return amplitude of this state upon acting by this Hamiltonian. In other words, it's e raised to minus IHT acts on this thermophile double state. And you compute its overlap with the original TFD state. What you get is nothing but a combination of the partition function at imaginary time, normalized by the same partition function at temperature, and then you take the mod square. That's the very familiar spectral form factor. The whole point is that this is something that I did not know, but at least the quantum chaos community knew it for a very long time. Is that if you just look at this particular object, it knows about the fine-grained, in fact, the finest-grained UV data of your quantum system. In other words, it knows about how your quantum system should behave for essentially forever. It's a remarkable thing. In fact, even in quantum mechanics, such a notion exists, and this has found, of course, many applications in recent times. We want to understand things about quantum gravity, and in particular about black holes and so on.
Sorry, so IHT, what time is that? In the black hole example, that's the time that goes forward in both?
That's the time that goes forward in both. Yes.
I see.
Yes.
I see.
Yeah, the other one is it just leaves it in your island.
Yeah.
Good. So, well, first of all, I should apologize again for the picture. I would ask you to ignore this bump.
I'm so sorry, Arnab.
Yes,
we'll talk about it later.
Yeah, sure.
Can you explain why this the amplitude is the Z beta plus IP by Z?
Oh, this is something, well, let me see. So what you do is H is H1 plus H2, and you know H, so what you know is this N1, H1 on N1 is basically E1, En1 on N1 to be the eigenstates, and similarly for 2. So what you do is you take this CFD state, which has this up to some weight, the N1 tensor N2. So I know how H acts on N1 times N2. And these are, of course, two copies of the same Hilbert space if you want.
I get.
And then you just. So this is just, I'm just putting it out because spectral form factor is something that is related directly to what people sometimes call quantum revivals. The terminological issues sometimes are quantum revivals. So this is what, so you start with the state and you ask the question under Hamiltonian evolution, can the state come back to itself? So that amplitude is measured by this. And in fact,
I didn't even know this. This is very nice.
And in fact, this is a very nice way of understanding that long-time dynamics can give you UV data, because I can prepare a state meticulously with arbitrary UV specifications. But quantum mechanics will again regenerate. This is like a reincarnation if you want to be particularly spiritual about it. But anyway, this is there, and it happens in just plain garden variety quantum mechanics, which now people can actually simulate and see, and it's very nice stuff.
But of course, it comes back with all this sometimes.
Yes.
For any reason.
That's right. And in fact, spectral form factor exactly computes that. Good. So sorry, first of all, again,
I'm sorry, I'm confused with this picture here. I mean, so this spacetime one wants to say that this is dual thermophile double state, right?
No, I don't yet want to say that. Okay. All I was saying there is that there is a quantity which I'll now talk about.
So
spectral
the
form factor.
internal black hole being dual to thermophile double state, that's something you would like to question also.
Not necessarily I'm going to question that yet. All I'm saying is that so if
I'm not necessarily asking about this slide.
Yeah.
I'm just asking, I'll say something if you agree with this. Then, I mean, I'm confused about this, teleportation thing.
Yes, wormhole.
There, just the fact that this eternal black hole
Yes.
is equivalent to thermophile double, and from thermophile double, people can teleport one side to the other, right?
Correct.
People have done that on the computer also.
Correct.
So in that sense, how is this picture consistent with
So
that?
I will not talk about teleportation. What I'm talking about is revival. This is different.
No, here it's fine. I'm saying how is this whole intersupposal? What will you say about that?
So here, if you take this literally, here you could say that the thermophile double state is something I can sort of get out of a configuration like this. So no
It's a
wormhole,
teleport, right?
no wormhole, no teleportation.
Yeah, but I know it teleports.
Which one teleports?
The thermophile double state.
Yes, but I'm not talking about thermophile double state per se. See, what I'm saying is the following, that here,
How much of conventional understanding are you giving up? That's what I'm asking.
no, I
When you
don't think,
propose
I think he's giving up on eternal black hole.
yes,
He's not trying to simulate eternal, he's trying
That's
to
right.
simulate only one-sided.
exactly. So let's forget about eternal black hole.
I see. So you're thinking more.
Eternal black holes do have horizon. Sorry.
Yes, of course.
Sorry.
No, please. So I guess you're thinking of black holes from collapse.
From collapse, yes.
And okay, maybe in the spirit of fuzzballs or whatever, firewalls or
Right,
whatever. You say maybe at late enough time, who knows what the undo vacuum is, or if it's something else backing up.
Yes, yes.
You bet is
Somehow,
Maybe
suppose
wall.
somebody
You
gives
get a
this
wall.
wall. Yes.
fine. All right.
Yes. Then the question is, what do I get out of that? So there should be a clear, yes.
Just in an order one amount of entanglement between sides and spectrum, right? You would still have a teleportation, but it would not be like a geometric one, right? You can see the bump.
But that I think is outside the scope of anything I will say. It's much more complex.
The point there is that you can explain this teleportation through geometry.
Yeah,
That
I
is
think you would probably have teleportation kind of thing, but it would not be like a geometric thing. Because the amount of entanglement here seems like an order one.
Yes.
Is this right?
I think so, but I mean that I have no way of quantitatively,
I think they may not have gotten GP.
But what do you mean when you say it's order one entanglement?
I mean, if there's a scalar field on the geometry, that will itself give rise to something. Scalar field on the side will make
Actually, with the conventional two brick wall model, you have no entanglement.
You have no
You
entanglement.
you put Dirichlet boundary conditions, like extreme violence on the Minkowski background.
Yes.
I don't know if that's what you like to do.
I think for now, these statements will not, because I can't really make a quantitative statement to what's saying, so it's effectively the same thing. Yes.
It's sort of very drastic.
It's very drastic. You're breaking equivalence, just go and hit something.
There could be something completely quantum. I mean, even in the big wall stuff, tunneling. I mean, there's nothing classical. There's no
You mean geometry.
Yeah, there's
So
no geometry.
So exactly. So this is some geometry, this is some other geometry. There could be some quantum effects between them. This I cannot rule out.
It's a question of what state the scalar field is.
Yeah.
Right,
Yeah.
right.
I mean, all I'm saying is you may not want to, and it may be beyond what you want to do, but at least what to try and make sense of entanglement and so on. He did this very drastic thing,
Yeah.
right? He said, I'll just put a brick wall and I'll say Dirichlet boundary conditions for the scalar, and then I get a tensor product Hilbert's place.
That was
You know,
my.
and then you don't have any entanglement. That's what
Right.
we tried to do.
I thought that one.
Or maybe I'm wrong, but that was my.
No, I think that is, I'm not sure whether Cook was thinking so much about entanglement,
But
but
at least he computed the.
computed the entropy,
Yeah,
thermal entropy.
and
Yes.
then he was not.
Right, so the thermal entropy is not zero, right?
No, it's not zero.
Yeah, but I mean, there's thermal entropy and quantum entanglement. Okay. And I'm just saying he put Dirichlet. So then there was nothing beyond.
Right.
There was nothing beyond. Okay.
But I mean, it's very hard to really precisely talk about that without, knowing what this object is, how it is created. So it's really good. So, this is a picture that I think that was the first time well, at least to me, it was pleasantly surprising. I'll try to explain why. But before that, I'll try to, I'll ask you to ignore this name here. It's not really there, but anyway. Shimon has made a much better plot and then played the country without giving me that, so I can't. Anyway. So this is very simple. The standard understanding is that you look at the spectral form factor at various time scales. In fact, it's a log plot. That's what you're supposed to do because you can keep up with very, very long time scales. What you see is that there's an initial dip, well, that's not surprising. You do something to the system will start relaxing, and therefore there's a dip. And very long time later on, if the system is has a gap, then it will saturate to some plateau, some non-vanishing value. That's also not surprising. What it does in the middle is the thing that that is non-trivial. And in fact, the thing that surprised me is that this system, which I'll come to in a bit more precisely, is actually shows a linear ramp of slope which is very close to 1. This is the part that is surprising because in random matrix theory, you actually get a ramp you get a linear ramp with slope exactly 1. But it's not just a numerical finding. For random matrix theory, you can actually show that this is indeed the case. For us, we cannot do that. In fact, this is, the system that I'll describe is not a random matrix theory, which I'll also mention. But there is a notion of chaos. There's a notion of, in other words, spectral correlation or spectral rigidity. There's various terms that people mention.
This is the result for what system?
A free scalar field theory, which I'll come to in a moment. Yes.
What sets that to yes?
Oh, that's just the number of scalars in this case you have. Here it is just some order 1 number. It is not interesting in terms of large encountering. But this is the probe system, so it's not really cannot really gravitate and cannot do those things that gravity does. So it's for a probe scalar in this brick wall geometry when the wall is very close to the horizon.
But then, I mean, that time scale itself cares about entropy, right? I
Which
mean,
time scale?
the time for which the ramp exists
Yes.
is, I forget what it is, but it scales like to the,
1 by G Newton.
Yes.
1 by G Newton, no?
Yes.
Yes, but here I think
Well, I
you're
mean,
right.
Here.
Would it be any, I mean, if you had order 1, everything wouldn't it just ramp up?
No. So for example, here, this time scale roughly is when the Heisenberg. This is roughly speaking the Heisenberg time scale, which knows about the minimum gap of your
I
spectrum.
see, so you say there's still a difference.
Exactly.
There's the quasi-normal, which you will have presumably move
Right.
the ring down,
Right.
and then that's of course fast, and then you have this.
Then you have that. Then there's a gap
No, I
which
understand.
gives you this.
This gap is because your scalar is in a box.
This exactly.
So I mean, maybe the
Yeah.
question, how is it that you get this kind of plot from this geometry?
What ensures it?
What are you computing?
Yes, I'll come to that. So, but before that, let me just make a.
Even the definition of that was in some field theory.
Sure. I mean, you can take it to be a quantum mechanics also. So what I will do is really quantum mechanics, not field theory. I mean, or first quantized version. But anyway,
You have an H bar in the bulk.
you have an H bar in the sense that this is a probe scalar, so I can express everything in terms of 1 over G Newton.
I'm wondering if Sandeep was asking, what is the parameter that allows you to say that it's a straight line? Is that H bar or is it number of scalar fields?
It's the H bar. Yes.
Okay. That's more understandable.
Yes. That's right. So this is a lazy thought that I will just show, or I mean, this was sort of my first thought, if you want. It's a very, very elementary thing, and I don't have anything precise to say after this. But I'll say the following: if I look at this plot, which is what let's say a nice quantum mechanical system should do, by nice I mean unitary as well as black holes. The first reaction is that okay, this part of the plot which is decaying comes from an ingoing boundary condition. That we know. I mean, that's very easy to do even with gravity. This one comes from if I have a particle in a box, like a reflecting boundary condition. So the process of this two qualitative features, which typically people understand in random matrix theory as two different saddles, transition between two different saddles, can also be sort of engineered by changing the boundary condition. So you quench your boundary condition, and then you have whatever you want. So this is reverse engineering, of course. But anyway, I just wonder whether this is a useful notion for some system.
So 1 over n, what I normally think of as 1 over n square will play the role of H bar for your bulk scalar field,
Yes.
right?
Yes.
So is that dip at order, the time of order log of n?
Which did this one?
Yes.
Yes. Yes. Exactly. Good. So this is the system. Start with BTZ, this we all know and love. BTZ because this is where I can solve my scalar field equation exactly, nice hypergeometric functions and so on. And that's the scalar field equation. The mass I'm going to take to be 0, but it doesn't really matter that much. And then what you do is you try to solve for the scalar field with certain ansatz, like this. Here is a radial part, and then there's a time part and the angular momentum part. And this is a very crucial part. You plug it into your equations, and you get some simple enough ordinary differential equation with the potential and so on. And then you solve for it. Right?
So,
It's very simple. Yes.
so what you're trying to do the quantum mechanics is like doing quantum mechanics in an annular billiard
Yes.
boards.
The board is what?
Yeah.
Exactly. What period would you?
I didn't understand that word. Why is the million? Sorry, why?
It's a hard reflection
I see.
here. There's a hole in the middle,
I see.
and you have some.
Quantum fields on that.
Yes.
I mean,
But it's doing quantum mechanics, so it's really like.
Is it quantum mechanics?
I'm going to really do quantum mechanics in the sense that this is a first quantization. Only the single particles.
So very massive particles.
Yes. So only the single particles.
So the spectral form factor will be just for quantum mechanics, is it?
Yes. First quantized form. Yes. Good.
So fixed number of particles, some number of particles.
Exactly. Exactly. So then
Epsilon, there should be some epsilon.
yes, in the boundary condition. So here is the solution. That's fine, simple. We all can do that. And then the boundary condition is also simple. We know the first one. This is just the asymptotic boundary condition. You say that your field goes to zero,
The
normalizable.
mass of your particle is what?
We have chosen it to be zero for the numerical purpose, but the number I don't think matters that much. Now, the condition at the non-trivial surface is basically that the field is also zero. You could put, in fact, some other non-zero number, but it's a Dirichlet number. And this is where the information of epsilon is, because for some reason I have chosen R0 here. R0 is my epsilon, if you want. So you impose that, you get a bunch of boundary condition that you have to solve, and you solve it, which gives you a quantum spectrum. In other words, a spectrum that is quantized, and you find that spectrum. This you have to find numerically, but you can do that, and you can do in fact slightly better, which is something that we did later with Schumann. You can unsurprisingly, you can express this equation as a quantum mechanical Schrodinger equation, and then you do the usual WKB. The nice thing is that the WKB answer gives you actually some, at least an analytic answer for the spectrum in a region when epsilon goes to zero, meaning when the cutoff surface is very, very close to the horizon, gives you a nice close analytic function, which you can use. In fact, we did use to our advantage later on.
So what is N and what is M?
Sorry, yeah, that's right. So N is, so M, sorry, unfortunately, I think I'm switching conventions. So this J is M.
Okay.
J and M is the angular momentum. And N is something like just the quantization that comes from particle in a box. Number of modes.
Sorry.
Essentially. Good. So you get some function which is a combination of this N, M, and also knows about the epsilon. That's
So sorry, WKB you're saying works at large N or at finite N?
it works better
Close to epsilon going to zero.
close to epsilon. As epsilon goes to zero, it actually works for reasonably large N.
But in the region of the horizon, it probably works for no matter what N is.
Yes.
But if you want WKB to work everywhere, you
No,
probably.
no. Then I don't know. Then it will not work very well.
Yeah.
Then it will not.
So you're
work
doing
very
some
well.
matching. You're matching onto WKB.
Exactly.
I see.
Exactly. And even on top of that.
And then you're just saying that proper energies are large
Precisely.
because of redshift. Right?
Exactly. All that. Good. So right. So this is
The epsilon going to zero limit, these things go to infinite. Omega.
no, actually this function is this is something called a product log function, which is, well, Mathematica gives me this in terms of this, but so W of Z is basically a solution of Z x raised to EX.
What happens for epsilon going to zero?
What happens when epsilon goes to zero is I'll show you. I think omega goes to zero.
You get a continue.
You get a continue.
Omega goes to zero.
The gaps close very, very fast.
You want to basically reproduce quasi-normal type wave.
Yes.
You need some sort of cut.
Yes. That's what will come.
Yeah, and for a box, it's discrete. There's epsilon.
Precisely. Good. All right. So here is what it is. So, for example, this was your question. What happens when? Okay. Let me go step by step. So, if you compute, let's say the modes, I'm just showing you here one particular mode, omega for n equal to 1 and j. I'm just particularly showing j because that's the non-trivial part. With respect to n, these modes are somewhat linear. So less interesting. So the thing to note is that there's an interesting curvature here in the omega versus j angular momentum plane, which is to say that there is non-trivial level correlation. That's what level correlation means. It's no longer linear. And in fact, it's this behavior or it's this correlation, if you wish, that gives rise to this ramp of, let's say, slope linear, so slope equal to 1. And the bottom line of all of this is going to be very simply the following thing, that if you take epsilon close enough, you see this behavior appearing and then this ramp appearing, which has slope very close to 1. And then it's very stable. No matter how much more you try to take the wall closer and closer, it doesn't change.
So what is this form factor? How are you computing it from whatever you did so far?
So we computed this omega, right?
Yes.
And then I compute just e to the minus beta omega, sum over all the.
Why? I mean, why is that the right? I mean, that's some thermophile double, and this is.
No. So thermophile double, I just introduced to tell you that spectral form factor is something I can think of in terms of revival of thermophile double.
Okay.
But let's move that aside.
Okay.
If I just look at
quantum mechanical,
it's just some
you just
quantum.
want to compute some
Exactly.
observable,
Exactly.
and then some expectation about the observable being this.
Exactly.
Why? I thought that is specific to some that thing there.
What thing there?
The SFM.
No. So spectral form factor for a quantum chaotic system is supposed to be here. That's the bottom line. And if you take random matrix theory, you can actually show this at many parts of this analytically. Outside random matrix theory, you can't do so much. But yeah, you have to go and compute.
Or on a simple laptop, which you
Or on-
yes, it's a very robust feature.
Yes.
But this is a quantum mechanics in some gravitational background with some boundary conditions, right? Not the
Sure.
quantum mechanics of the boundary theory.
No, not the quantum mechanics of the boundary. That's right.
What is the temperature of your system? Is it the black hole temperature, or,
We can set it to arbitrary. Yes, we can set it to black hole temperature.
but you don't need to?
So that we don't need. That doesn't make a difference.
And what is you're obviously seeing level repulsion.
Yes.
Right?
Yes.
And intuitively, what is the argument from the shape? So in random matrix theory, of course, you have the famous sign, right? And here somehow your billions is generating level repulsion.
Yes.
What's up? Can you explain?
I don't really know because in random matrix theory, as you said, you have the sign kernel and everything is gold because then you can prove it's much complicated, but still can be proved. But there are many other systems where you do not have such a neat formula. And in fact, your level repulsion may not be as strong as random matrix. In this case, in fact, it's not. It's somewhere in the middle. But in those cases, I guess you have to go and find out whether you have enough level correlation to generate an interesting correlation. So all I can say is that there is a non-trivial level correlation that emerges when you take the wall very close to the earth. If you start taking it farther and farther away, then these lines will become straight lines. They just become a bunch of harmonic oscillators. And then the spectral form factor is just some very simple thing.
When does it become harmonic?
So if you
Take it very far away.
take the wall far away, then the spectral form factor is, well, to my dismay for harmonic oscillator, also I recently calculated spectral form factor, which I guess you could compute in, I don't know, long time back. But then for harmonic oscillator, it's just very nice, something like this.
Because of the underlying fundamental.
Yes. And these are the, whatever, 2 pi by omega, the frequency.
I was sort of asking something similar because if you just take random matrix theory and you start thinning out the randomness and so on,
Yes.
you get a lot of different kind of structures.
Exactly.
But here you more or less after coarse grading or averaging, you saw.
No, we have not done any average.
No, I know you haven't. But the raw data suggests a nice ramp,
Yes.
right?
Yes.
After I average over the
Exactly.
fluctuation.
Exactly.
And so it's kind of interesting that you.
Yeah, that's my submission also. That I thought initially that this can't be interesting, but it is.
What is the?
Yeah.
I was going to ask, what is the distribution of this level space?
I'll show you. Yes, it's not going to be that interesting, but yeah.
Bigness summarize.
You won't be. No,
Is
it
the-
won't be Wigner.
It's not chaotic from that point of view.
Yes.
Okay.
So it's not chaotic in the strict sense. It's not random matrix theory in other words, but there is a ramp which is very, very close to what see. Yes.
So in the usual type of, setting where you have some SYK model, single boundary, let's say, and then you want to have some goal description.
Right.
Then whatever this calculation is in the gravity would give you something like that, but everything would be smooth, right? All these
That's
things
right.
would be smooth.
That's right.
And then the one loop effect on that would give you some zigzag.
Correct.
And that is how one understands this zigzag pattern in the boundary, and that's why
Yeah.
you expect this. Yeah. I'm just saying whether I'm understanding it correct.
No, I think you're right. Yes. Here, exactly, we are not in that sense doing anything to gravity. So you might say that, in fact, it's correct thing to say that this has nothing to do with gravity because these are scalar fields propagating in a geometry. So other than it's coupled to gravity, really has nothing to do with gravity. You could say that it's a one loop determinant effect.
In the gravitational calculation, this time scale at which the ramp sets in is equal to 1 by t, right?
Yes.
And here, if I understood you correctly, you said it's something like log of 1 by t.
No. Where the ramp starts.
Huh.
No, it's determined by h bar. That's present in the bound.
Is it e to the 1 by t?
I think it's well, yes, I would say yes, because this is a log plot. Then yes. So h bar, I mean, whatever you get in 1 over g Newton in gravity, here just replace that by h bar.
Okay.
That's
So it's
what
still
it is.
easy.
Yes. Yes.
Okay, now maybe I'm wrong. Basically, the quasi-normal decay means that the disconnected part dies exponentially in time. And the connected part is down by a power of e to the s, n. So basically, at t of order log n,
Yes.
this will
It happens. Yes.
right? That's when it starts to.
Sorry, I
And
remember.
here it will be h bar. but-
Here it will be h bar.
I remember from this Stanford paper that this dip goes like 1 by t. Yeah, right now it's not exponential. Power 1.
No, but this is a log plot.
Sure. But even
So
somebody
in the log plot is a power law.
It's governed by the quasi-normal. The
Right.
connected part.
then that's very early time. As Ashit is finding out, it's very, very early times, it's exponential. Then it transitions to power law. And then that you have to compare ramp with the ramp. So that's why the ramp sets and everything.
Otherwise, it will be power.
Correct.
I see, okay, sorry.
But I think, okay, but even from your point of view, it's at an exponential
Yes.
because the h bar is one.
Exactly. So replace a g Newton by 1 over g Newton by h bar. Yes. So in that sense, it's not related to g Newton physics, but yeah, can think of it as fluctuations if you want.
In fact, the power law part is non-universal. If you have non-Gaussian matrix models, then the power law is not changes.
I know G will be.
Yes.
Arnab, you said
Yeah,
you
that
did
one
the
becomes
first quantized calculation, right? But now that you have the spectrum, doing second quantized is just like
That is
taking
right.
many states.
Of
like
course,
that, and
of
then
course.
You could do this.
Yeah, of course. No, see, the reason I'm doing it is because of the following thing. So this is a free theory. So getting the full partition function is trivial. You just exponentiate and get it. If you do that, you will lose everything. The reason is simply because, in fact, this is something that you also do in all these works with CFT and chaos and so on. Because if you sum over all states that are present in your spectrum, you may find out that. Okay, let me give you an example. Suppose you start with random matrix theory. Random matrix theory is supposed to give you this. Now imagine a system which is basically multiple copies of the same random matrix theory. Compute the partition function and you will see nothing of that sort.
Well, that's your problem, but that's what you are supposed to do, isn't it?
What am I supposed to do?
Quantum system is a second quantized system.
Yes.
The fact that you lose it, I mean, no one can help.
No. That is true. You can say that.
Why we are attached particularly to this picture?
No. All I'm saying is that unless you look at, for example, okay, what I'm trying to say is you may lose out the interesting features if you look at the full multi-particle sector, because then if there are multiple random matrix theories, they will lose out the mechanism of repelling each other. if you sum over all of them.
But I think.
But what you're saying is also true. I mean, I agree that given a system, you should actually compute the multi-particle sector, the full thing, and then look at it. All I'm saying is that this is a free theory. If I do that, I'll lose everything. But the single particle sector does show this. That's all I can say. It's a technically correct statement.
No, but it could, I mean, his point is well taken. Finally, you would have to do it for the.
Finally, you'd have to do it. Yes.
But it's true that the free theory is a very special limit,
That's
right?
true.
And then oftentimes, if you have extra symmetries, to see the chaos structure, you have to unfold. For
That's
example,
true.
in the Wigner summaries, and
True.
and so on and so forth, right? So maybe for that reason, maybe you have to look.
Yes, sometimes you have to project onto certain
I don't
sectors,
know. I mean-
otherwise you'd not be able to see it. So that's the analogy I can give.
I mean, you may not expect chaos and so on in a free field here.
Exactly.
So
Which
Is
is
that all these lessons, what am I doing these lessons? If one lesson is that there is no chaos.
yes. I mean, the no chaos is what I would expect.
Yeah.
Right? I don't exactly know what to tell you other than the following thing. That suppose there was a way of taking interaction into the picture, which I don't know how to do yet. Now, because the single particle sector shows me certain chaotic features like this spectral correlation and so on, it's not unlikely that the interacting theory will start inheriting this. In fact, make it stronger. Because if I add interaction, intuitively I would think the system will become more pure rather than integrable. So from that point of view, this could be interesting. But again, this is a comment. There's no calculation I can do which will show you this.
It's very hard to do a honest to goodness
Yes.
calculation in the lambda 5 theory on your
On ADS.
on cutout.
Yes.
Yes,
Yes,
very hard.
exactly. But I have some comments about that much later. Anyway. No, not precisely. Yes, if I could do it, I would do it. It's the statement.
But perhaps your hope is that once you include those
I
interactions.
hope that this is not just a fluke. That this observation is just not.
I mean, I guess I'm a bit uncomfortable with the zero order fact that all these calculations usually one does in the boundary theory, and one learns that the boundary theory is, chaotic.
Mhm.
and so on, right? So, but now we are doing this on some fluctuation on the gravitational,
But at the,
some one loop effect.
correct, it's a one loop effect.
So then,
But if I, for
begin with,
example,
I'm not even sure whether I expect any of this type of behavior.
Not in the
maybe it's
multi-particle
something, it's a
sector.
lesson
I
that I
agree.
missed, but.
no, I agree, not in the multi-particle sector. But so if you leave that out for a second, the moment you talk about properties about partition function of either the bulk system, just simply ADS-CFT tells me that there is partition function of some sector in the boundary CFT. There are certain operators which are probe operators whose partition function I'm computing. Right? I'm not doing anything to the original CFT, so to speak, but these are certain probe operators.
So you're saying that somehow this split between the classical and one loop, I can map it to some particular sectors in the CFT?
I think so. Right, partition functions map right under the duality. So since this is a partition function, this must map to a partition function in the CFT. That's all.
The standard spectral form factor in the dual CFT, you try to compute its one to direction.
Yeah.
That would correspond to the full multi-particle count.
That would correspond to the full multi-particle. Yes, exactly.
Can you do one particle? You get similar behavior for one particle?
This I think is the one particle.
One particle.
Yes.
So at least as far as quasi-normal modes go, that's what's relevant. So it's just the poles.
Just the pulses. That's
So,
right.
I mean, whatever something deep or not, you would expect a continuum at least
Yes.
in this one particle. And then because things are coming close to each other, you might get some repulsion. Doesn't sound so.
Yes.
Shiraz, what is this? I didn't understand. So what is the I should know this, but what is the coming together? I just thought he's put it in a box, he'll get some spectrum and
He'll get some
weight and so on.
But we know that in the black hole background, these quasi-normal modes have poles, but off the real axis. Here he's going to get poles at any finite epsilon, but on the real axis.
Exactly.
Okay, so you can ask, how do you imitate a pole off the real axis by poles on the real axis? And you get basically a spectral density. That's the kind of thing that you
Continuous.
It's a little like a decaying particle comes with a spectral density, and therefore decays. So the behavior that will reproduce poles off the real axis would have to be a continuum.
Yes.
So how is the gut produces a pole of the real axis?
That's what I'm also not.
No,
able to-
so this I'll come
That's what
to.
I was also not.
You know, if you look at spectral function of, let's say, hypotheory, something like this, you have the continuum limit like this, right? I mean, the continuous part. There are poles here, let's say there's a mass square, and then beyond that, beyond the threshold, it's just a continuous, right? But there are sometimes what is called nano resonances, which are particle-like resonances. They are in the continuous part, but they have a decay width.
That will be.
So this will have what I think Shiraj is saying, the quasi-normal modes. I mean, exactly something like this.
Oh, you see this kind of thing.
Yes,
I see,
it's exactly that.
So they're part of the continuum and then they have the grid.
So you can read out in other words, I mean, in some sense, one of the bottom line is that from the normal modes, once you take the wall very close to the black hole, you will actually see the black hole quasi-normal modes emerging.
Okay, but what is the analog of your continuum here? Because in the single particle, as Shiraz said, you just get nice poles,
Yes.
for N and M or whatever, as you said, along the.
So right.
then,
So
yeah.
here the poles will be like this.
Like
These are
that.
my quasi-normal modes.
Ah.
Sorry, these are my normal modes.
Ah,
And then the claim will be, as I take epsilon closer and closer to 0, they will come closer and closer. And depending on what your resolution is, you might at some point declare that this is a continuum. Once you declare this is a continuum, then you compute the spectral function, which is the jump of the correlator. And that jump will have these poles, which are the black hole, which coincide with the black hole quasi-normal.
See, so somehow it's, once you get a cut, it starts looking like a pole.
Yes.
I have to understand this, sorry.
This is imaginary part.
Some
Which is the imaginary part?
That graph that you.
Yes,
plot
that's
is
the imaginary part. That's the
Poles
imaginary part.
of the real axis do not give you imaginary part. It will give your part.
No, let me come to it. So this is the imaginary part of the Green's function, which in this case will be equivalent to the black hole Green's function. So the black hole Green's function will have poles
But I was
with
thinking,
the ingoing boundary.
but I was thinking maybe it's wrong analogy was that the Lehman, in the Lehman representation of a propagator, if you get a pole off the real axis, you have a wave. Yeah,
In the imaginary part.
just in the Lehman representation. You write it as a sum over poles. You can
Yeah. So the spectral density.
spectral density. So
Yeah.
you take the thing off the real axis, that gives you a continuum. Right? That's why you have. I was thinking of that.
I think something like this, yeah. This is also something I don't completely, I think, understand, but it
But
happens.
I don't understand it well. I see how it.
Like bright ring then.
Right.
Right, yeah,
Exactly. It's a bright big part. Yes. Okay. So when am I supposed to stop, by the way?
You're not supposed to.
I'm not.
Actually, you're here tomorrow.
Yes.
So we can have a continuation.
He's going to talk.
He asked me to give another talk. Okay. No, I can.
No, I have to quit. I have to quit it, but you guys should go on.
What time? What time?
To 10 to 1. Because I teach at 2.
All right. So,
But no,
but one of the major thing is there, and the other thing that I actually do not completely understand is this thing. But it happens. I mean, there's some calculation that just gives.
Yeah, it would be nice to see the calculation.
Yes. So good. So let me go ahead. I mean, go through this. This is not very difficult. This is what you get. Sorry, this is what you get from the harmonic oscillator, or if you have a linear spectrum, and essentially like this. And this is what you get if you replace the wall at a part of a distance. No surprises there. Now about Omkar's question. So let me just make one quick comment on this. Is that if you, for example, compute the level spacing distribution of the full spectrum. The full spectrum will give you a Poisson, which is what you expect, right? Because that's a PQ. But if for some reason you choose to still understand, or you want to analyze what happens to the spectrum as a function just with respect to the angular momentum, what you get is something like this. It's clearly not
for fixed J, you look at.
for fixed N.
Yeah.
For fixed
J.
Oh,
J is what generates all these non-trivialities.
It's like the K dependent. So the thing which you have the pole.
Right.
It is above the equal.
So this is the important part, and this has some level repulsion, although nowhere close to magnetized here. So this is not random matrix theory or conventional chaotic system or strongly chaotic system.
This big deal, sir, because it's numerical.
Yes.
Otherwise, it will be smooth.
Otherwise, it will be smooth.
What about for fixed J? Because often you'll see the
So for
repulsion
fixed,
for fixed symmetry sector.
yes, no, for fixed J, you will get a Poisson because that's just some linear function. Well, it's not analytically linear, but it's something that looks very linear.
Because you still have the area growing like in hyperbolic space, right? So all the ends are accumulating there.
Right.
Okay, but it doesn't happen.
Yeah, yeah. So there is something more, I guess, improvisational stuff that you can do, and I'll just be very quick because, well, it's something I think here that the story will be kind of put in what we get, so it's not really surprising. But you can again, I mean, sort of motivate yourself a little bit more from the first ball kind of story, and you say that okay, this boundary condition was a bit too restrictive. In fact, no real first ball solution actually has this kind of profile. They have, in fact, somewhat angular profile. So you could say, okay, can I impose, sorry, can I use a boundary condition which depends on the angle now? It's not a circle, it's just some random curve. How do you characterize a random curve? That's a bit tricky. So what you can do, or what we did do, is that you can take this function, which is a function of an angle, do a Fourier mode expansion, and the coefficients are something that you choose from a distribution. So let's choose them from a Gaussian distribution.
I didn't understand. Sorry, what you're changing a boundary condition?
Yes. So what we are doing is on this circle, instead of saying that phi is 0 everywhere, I'm saying that phi is some function of theta, and this function is something I do not know what that is. So that function is you expand that in standard Fourier basis, and then you just choose the coefficients from a distribution. In particular, Gaussian.
I see. Choose random.
Yeah. So then it's not surprise because I mean you're putting in some random boundary condition by hand, at least in a controllable way. So what you get out will be a function of that. That certainly is not surprising.
So this level repulsion comes out because of this boundary condition. If you just put phi equals 0.
No, then what I showed you, they are true.
Okay.
So there's a ramp with this level spacing distribution.
Yeah.
But this you may wonder, okay, can I make it more interesting? And the answer is yes, you can make it more interesting or by putting in boundary condition. But there it's less surprising because you're just putting it by hand. So this is what you choose. Sorry, this is when you choose the coefficients from a Gaussian distribution with 0 standard deviation, which is to say what I just described. And then you start increasing the standard deviation. And then at some point you get a very nice Wigner-Dyson line curve. And then after a while, if you keep increasing the standard deviation, it becomes just a Poisson.
And this is you're changing your phi of theta or something.
Yes, yes, exactly. So this is the case where you have basically washed out every correlation. You have filled in every spectrum, everything, so there is no anything. I mean, the spectrum doesn't know about any correlation within it. Here, in some sense, the maximum correlation because you're putting in by hand certain randomness.
So this is the limit in which phi naught of theta becomes uniform.
This is the limit when phi naught of theta becomes uniform.
It chosen a particular phi naught of theta or you average overall?
No. Once you choose one, then you just stick with it. Yes, yes. But this is just these arrows just show that I'm choosing them from a distribution whose standard deviation is increasing. That's all. And then if I increase the standard deviation, you go in uniform, then everything is lost.
But sorry, in the spirit of fuzzball, I have no idea what that whole idea is, but maybe you have many microstates, each of them has a different phi of theta,
Right.
and then you should sum over a Gaussian random variable. And
Yes.
then you might have even a better chance of isn't that more the spirit of
Probably yes.
asking?
Probably yes.
Okay.
Probably yes. And that I think in this description that can be done.
Yeah.
But I mean, as I said, this is kind of getting what I want because I'm putting in enough randomness, you get what. And I mean, you put in enough randomness in the boundary condition, the dynamics gives you randomness. That's not very surprising.
So let me just go back and ask this question again. What do you mean, get what you want? How do you know what you want?
No. So say if you want randomness,
Ignorance.
if that is
But why do I want randomness?
So, for example, at least this is the story that we at least believe that black holes are post-thermal objects. In fact, they're the most thermal of anything that you can think of. So you'd expect that black holes will give you quantum chaos, which would be the strongest quantum. So the strongest thing that we know is random matrix theory. I think that's probably the rationale here or expectation here. But of course, I mean, if you come up and give an example which is perfectly UV finite and very nice properties, etc., and you do not find it, then I think the onus is on us to argue why that should be the case. But
So if one does this actually in the black hole background,
yeah,
the horizons and polygon
yes,
as well, then if one does this kind of, let's say, field and so on,
yes,
one single field,
yes,
what sort of
so then you see infalling boundary condition by design, this is what I was saying about the bound quench. Infalling boundary condition by design will just give you the decay arbitrarily long. It will never come back.
Okay.
That's also consistent because you're throwing stuff in, they're just going away.
But then would you say that it's not chaotic? The black hole is not chaotic because you don't see chaos?
It's not exactly. It's not an unitary system also because you're losing information. You're never gaining it back. Okay. So this ramp up. So there are two things. It could come back up here. Let's say it's finite entropy system. But how it comes back up here is also important. It could come back here like this. It could come back here, or it could go here, sort of like that. But these two are dynamically two different things. I think for black holes, it's expected that it will be chaotic one. And in fact, the lower dimensional calculations explicitly show that.
So what you're trying to reproduce, what is it that you want, is you want it to be even better than actual.
No. So what I want is that I'm not doing an actual black hole calculation.
Yes,
right?
I agree, but the behavior expected for the actual black hole is not what you're getting, right?
Yes,
that you will say is a better feature. It's a feature.
No, I don't think I'm saying that.
Why do you want chaos then? I mean, why do you want this zigzag and all that if you don't see it in a real time?
No.
If you just see the lying down.
Just one small thing. This is the spectral form factor
Yes.
for a black.
Yeah.
Right. So
I thought you would try to reproduce those things from
exactly.
this model.
The question is how much can we reproduce of that? And it is clear. First of all, it's not clear that whether this model should give you anything about this ramp up because where is the thermal property?
Right.
You might ask, right? But it turns out that this ramp exists. What does not exist is the Wigner-Dyson distribution, which is stronger for
in the actual black hole case.
In the
actual black hole case, what sort of graph do you get? What sort of picture?
No, so that's not an infalling black hole calculation. You see, there you have to be able to perform the full quantum gravity partition function calculation.
No, let's say you stick to the exact same model. You have this fixed black hole background, and you have this phi single field. Exactly the same thing, but with a boundary condition, not Dirichlet, but infalling.
Then it will keep going.
Okay, fine. So you get that, right?
Yes.
Then why is it that what you are getting is somehow? Yeah, then I'm mistaken as to what the. Yeah.
But just to say, see the ramp and the plateau, they are non-perturbative.
Yeah.
So we do know how to compute them other than JT gravity or some very simple we don't know how to compute them. So perhaps Arnab, but you should say your point is that if you could compute them in a black hole, the expectation is because it's a chaotic system, it might show some similar features.
And so non-perturbative.
Yeah, because these are all down in exponential in 1/g effects. So then the claim is we can't compute them today for a Schwarzschild black hole. But if you could, you might on general grounds expect. So if he gets it, he says he's. Is that right?
The claim is that now that you have this brick wall, it is somehow doing better in capturing non-perturbative effects. And
it is capturing some non-perturbative effects. Yes.
No, I just wanted to get the logic straight.
No. Yes. So the other, another way of saying it is that you're putting something ad hoc to the geometry, putting some ad hoc boundary condition, which is clearly not a perturbative thing in any sense. We don't know how to do that.
So you're saying this is what non-perturbative gravity is?
This could be, yes.
I see.
Sorry, and as epsilon goes to 0, this thing goes back to that shape?
What thing goes back to this shape?
Whatever you're going to get goes back to your where Abhijit was asking.
No. It's purely dependent on the boundary condition.
So even at epsilon equals 0, it differs from the black hole?
Yes, because it doesn't have the ingoing boundary condition.
But I thought you won't see any of it. If you really set epsilon equals 0, nothing on the outside will see the difference.
No, but there should be a signature of whether you are allowing the thing to fall into the black hole or you are allowing it to come back to you, right?
So what happens to this causality?
I think the time scale
Maybe it's very large.
go up to infinity.
Yeah. So that the
Fair
time scale
point.
cannot depend just on n, but also it should depend on epsilon.
No, you are right.
Sorry.
Well, okay. Maybe the statement is that exactly epsilon equal to 0 is not something I should think about here. But you can take epsilon to be as small as you want.
No, but I mean, there must be some smooth behavior as epsilon. I mean, something in this feature should start moving towards the.
You're saying compute the spectral form factor, which one?
This ramp feature. I
Yes.
believe this ramp is just coming from these reflections, right?
It's coming from the reflection.
Hits the wall and gets reflected.
Yes,
right?
yes.
So as epsilon goes to 0, causality, Ashirazi points out that this should come back later anyway. So this ramp should go off it.
That's probably true, yes.
So the time scale is a function not just of n, but also of epsilon.
Yes, you're right.
And at some log of epsilon.
Yeah, that's what I would.
Probably yes. This I don't remember, but
The 1 by epsilon.
You think?
Well, it's the other way.
It's roughly
No,
exponentially long.
let's go to
Causality question.
Yeah,
Is that what time?
it's log epsilon.
Yeah.
That's the usual, the
Okay.
delay is log epsilon. Yeah.
Yeah.
At least it's log epsilon, maybe, I mean, for the reflection, it's log epsilon, for your feature showing up, for the ramp you set in.
So that's actually.
No, yes,
right?
you're right.
So either it's log epsilon or, I mean, it's not e to the 1 by epsilon, right, for sure? Or-
I don't think so. I don't think so.
So, but just coming back, we should move on, but just coming back to Abhijit's point. Abhijit's point is all you're doing is studying a determinant.
Yes,
You're not doing anything deeper than that.
no.
So there's some limit where it reduces to the black hole. So now you're gonna have to fix an epsilon. Okay, fine. Just add that.
Oh, right, you can, sorry.
You're doing one loop around.
Just
a figure.
fluctuations.
That's what.
Yeah.
So far you
Oh,
did
fine.
free party.
Yeah, but
Yeah, but that's like the one loop determinant though, around the geometry.
Oh, I see,
Okay, but
okay,
it's
but.
not quite, right? It's like only the 1 part.
One particle.
but for the quantum mechanical action.
So what is the statement? Okay, so for the one particle action, you see a ramp at least qualitatively and so
Yes.
on. And then go ahead, you want this.
And then I think what Vijit and Siraj is saying that if you take epsilon to 0, then this point where the ramp was starting up will get pushed more and more.
No, but I would think that the natural choice of epsilon is
Blank scale.
blank scale.
Yeah,
So there's an end there.
Yes, I just a technical. I mean, there's a one parameter set of determinants which will start with a black hole and another thing.
That's what you are asking. Yes, I think that is.
Why is it expected and so on?
No, I think that
what
is
something, that even that zeroth order thing is helping me.
But let me ask you this.
Yes.
With an epsilon which is blank scale in proper distance, let's put it like this. If you put your brick wall a proper distance n plank away from the wood, every horizon,
Yes.
that will correspond to the onset.
Okay.
I don't know, I would have said a time log n or log 1 over g Newton. But you can correct me. The decay will begin to ramp up around that time.
That's what I want.
Yes.
And first of all, do you think
Yes,
that's a reasonable
yes, I think
statement?
so.
No, but is it right? Because you said something else at some point. You said that it happens at log n equals t, log t equals a. So what is the time of the recovery? That's a zeroth order question.
Yes. So that here, of course, I do not have n or g Newton.
No, but you have
What
h bar.
I have h bar, yes.
You have
So
h
it's
bar and you have epsilon.
exactly.
Epsilon. So, okay, I mean, I said.
You're asking what is the
as a
epsilon
function of
scaling?
Epsilon, yes, as a function of.
What is the epsilon scaling of it? Let me see.
I was wondering whether this log was a small dressing on top of an exponential scale. Because it's much of his time was just coming from his h bar, I thought.
I mean that is true. It will be log of h bar, that I'm sure.
And log of h bar, I think you. I had thought earlier you had said that
Yes.
he went like so that log t went like 8.
Sorry, log t went like what?
I thought in one of your graphs you were saying that the log t for for the ramp was n. So that t was exponential of n. Maybe I got that wrong. And n is 1 by h bar 4.
Yes.
So you're saying that the quantum effects at epsilon equals whatever, some reasonable scale, are giving you an exponentially large time scale.
Yes, true.
And then there's only a small log correction.
Yeah.
Is that right?
Yes.
Sorry,
I think so.
Yeah, even I find this confusing, but I had thought what you were saying.
No, that is true. Yes.
If we just do classical causality, we get a time scale that's clearly log epsilon.
Yes.
Okay, which is log h bar. If for a reasonable value of
Yes.
x. But I thought you were saying that there was a much larger time scale for this ramp.
Okay, yeah, shouldn't it just be the reflecting function, like particle reflection, okay, that's log epsilon.
Yeah, I was wondering whether the fact that he's got these many states.
Yeah. It could be different. It's not 100% clear. Because maybe I'm wrong. Because it's a level repulsion analog.
He's got a particle box. And he's got an h bar for that. And I was wondering whether that spacing is important.
Okay.
I think so,
That
yes.
spacing is not,
It's not entirely clear to me that it's the time delay, because.
No, you mean one is the classical scattering, which cares about the epsilon.
Yeah.
But what I'm doing here is really, once you know the spectrum, you
Yeah.
look at the minimum
You
gap.
look at the minimum
Yes.
gap. So the two are not the same.
The two are not necessarily
To
the same.
me, at least. So it's possible that you have a longer.
And what is the size of this minimum gap?
In terms of
H
epsilon.
bar. Yeah, in terms of both, if you don't mind, h bar and epsilon.
Why do you say H bar? I just said.
1 over x.
One over.
Because he's doing a quantum problem, and he's going to get a spectrum whose energies are spaced with h.
and it's h bar inside.
Is it h by epsilon or there's a log or something?
This I don't remember. I
Because
have to
it's
look.
like proper length. And the proper length has a log.
Yes.
No, the gap in the spectrum cares
Something like
about
that.
the
Something small.
size of the box, right?
Spectrum cares about the size of the box. Yes.
And the size of the box is like log epsilon.
Yes.
Okay, so but it would be nice to have those scales clear.
Yes.
What is the spacing? What is the spacing? Average
The
spacing?
spacing should be H bar divided by log epsilon.
Which is basically h bar. A log is 1. Please, Vicky. So the spacing is like 1. Well, if h bar is 1 by n squared, the spacing is like 1 by n squared.
So why is log epsilon we setting?
No, I'm.
Because it's a much smaller 0 or infinity than a power.
But it depends on the definition of epsilon, right? Why is this particular? Log epsilon is the distance, right?
Log epsilon is a distance, but I'm following Sandeep's lead and setting it to be blank scale. So
The
that's
distance.
the distance, yes, is blank scale.
Okay, so log epsilon is the length.
Let's suppose I do that.
Okay.
Then you have h bar, which is 1 by n squared, and then it's dressed by log. Let's forget about the log for now. So it feels like 1 by n squared. What does that time scale turn into, converted into time? It's just inverse of that. Inverse of that, right? Time n squared. Okay, so is that the time of the ramp or not?
The epsilon part, I'm not completely sure, but I'm sure it's order h bar. Log epsilon, I have to think a little bit, but it might be, yes.
The spacing has to be, whatever you do, right? Spacing has to be the size, right? I mean, the only.
Yes, the size is what Shiraj is saying is controlled by log of epsilon.
Yeah, but I'm just wondering whether I could be wrong because you needed this complicated wiggle profile, but even so.
Even if you leave that out.
Spacing has
that's
to
sort
be
of-
log epsilon.
Spacing is log epsilon, yes. But that's what Gautam is saying, that it's h bar over log epsilon, because h bar is the
Of course,
spacing.
I mean, h bar
Yes.
over log epsilon,
Yes.
sorry, yes. But that means that you get a time of this or that, right?
Yes.
It's log epsilon.
So
Which is the
that's
causality, there doesn't seem a separation.
between what? Between which
Because what happens in the gravity case is that because the ramp corresponds to a new non-perturbative effect, it's suppressed by e to the -1 over g, right? And that's why you get this long time scale. Whereas here, both time scales seem to be just this causality time scale. Log epsilon. No, log
So
epsilon.
what we were concluding was that there was a time scale n square, which came because of quantization of 4.
You're right.
N square. Okay, and then that was dressed by 1 over n.
Yeah, that's correct. I was a bit confused
Well,
because
I don't.
it was thought that there's a classical effect which just gives you some recurrence at log epsilon time scale. But maybe the observable you're calculating here is a quantum one. the spectral
Yes,
compact.
yes, I
So
think
that
so.
is not an important thing. So maybe in this case it's order n squared, time scale is order n squared. But if you computed a correlation function or something.
Of classical objects, then yes.
2-point function will definitely.
Yes.
Definitely.
Yes.
See that.
No doubt. No doubt.
Yes.
Okay.
I think so. I think so.
And we said it, I put it on.
It might wash out most of this, right?
You think, I see.
Okay, but then this is a clear distinction from the black hole, right? So black hole will see this feature in order 1 by e to the 1 by d, right?
Right.
Whereas you're saying you see the time scale order 1 by
Oh, 1 by what?
order n. Which
Order n square.
Yeah, which feature? It's RAM.
Right.
In gravity, you see it non-product.
Yeah, but that's from the saddle point.
Right.
This is just about the
Yes. I think so. I think so.
But even the determinant would only exist because there's this add-on thing.
Yeah.
No, but I mean, it's not a new saddle. I mean, in the gravity case, you have a new saddle, which is the,
No, it's there is no new saddle.
there's no new saddle.
There's no new saddle.
If the suggestion was that this cutoff is somehow mimicking that new
Yes,
saddle, then that is
exactly,
not correct,
exactly.
right?
I agree.
Yes, yes.
last question. I'm sorry, I don't know what we were like, but since it's so interesting and since
Yeah, yeah.
we've heard many talks and never understood them. This is our chance.
This is the most I've understood.
No names being taken. Okay. But since this is our opportunity, is there something we can do to help us finish this?
He's leaving on Wednesday.
It's giving a milestone.
Well, what's the second, I mean, there's another talk, why do you line up to, you know we never. It's there.
I thought we had the advantage of having him, so we might get myself, but I didn't realize. Yeah. Okay.
No, sorry. Initially, I agreed I'll stay for a week, but then something's come up and then.
Okay. Yeah. So maybe one possibility is just to continue with this talk and very briefly.
Yeah, that's fine. That's fine. That's fine.
How long do you think this talk is?
Well, I mean, I think the interesting parts are. I can try to sort of tell you the message in very quickly, and then maybe have a discussion. That could be.
I'm gonna leave in 5, but you must go.
I'll catch you later. At some point.
Sure.
No, but I think what you're saying is right, that it is of course there is no new saddle, so it's not going to be like black holes or the way the saddle changes and so on and so forth. It's there in this sense. Once you start with the brick wall, you can think about not having the brick wall. So that's what I was trying to say, that if you impose ingoing boundary condition up to a certain time scale, that's one saddle. The moment you remove that boundary condition by the brick wall or the Dirichlet reflecting boundary condition, that's another saddle.
I have one last question that I have.
Yes.
If you have a Gautam's billiard ball, but make it a slightly funny billiard, the kind that would give you chaos, a billiard table. Okay. Now, as a function of h bar,
Yes.
and the size of that billiard table, will we get similar way? I replace epsilon by the size of the log epsilon by the size of the billiard table, and h bar is h bar. Will we also there get similar?
Yes. I think so. I think so.
Fine. Then I completely understand.
I think so.
Yeah.
Yeah. If you want, I mean, yes, this is like a analog of billiard ball in areas.
Yeah, it's very close because as Gautam said, it's just one particle.
Right.
We've got particle, the spectrum coming together because of h. Okay, so you see something. Fine.
Yes.
I get it.
Yes. That's right.
That system may be chaotic.
Yeah.
Probably.
Yeah. Maybe we can find a billiard table that's somewhere between regular and something like
Oh yeah. That depends. I mean, how you make the billiard ball.
Okay, yeah.
How you make the billiard ball determines a lot of things.
Yes. Okay. Good.
Yes, good. So the last thing I wanted to say is about the quasi-normal modes. In fact, because we are in ADS-CFT, we are in ADS, we can use ADS-CFT, compute the 2-point function. So this is what we did. And I just want to say the following thing, that this is sort of a pictorial way of showing where the poles of the Green's functions are. That's where the normal modes are, which you can already determine. But this figure is just to tell you that if you take epsilon closer and closer, the poles start coming closer and closer, which is what I am showing here, right? And well, this is some quantitative estimate, which because we have the WKV answer, you can sort of pin down how it depends on epsilon and so on and so forth, etc. The only thing I want to say here is that if you check how poles are coming close in the angular momentum direction, it's actually very fast compared to in the other direction. In one case it's log, and the other case it's
This is also
Longest to
interesting. Why is it so fast? So we were guessing that it would be like log because of size of box, right? So say his spacing of poles,
yes,
the spacing between them goes like log epsilon is a function of n,
right.
as you would expect because radial size of it. But in this J, is it that box is growing bigger in a power law way? Oh, that's it.
It's probably yes.
No, it's not. Right? Why is it? Help me understand why that epsilon.
The second graph.
So this is you count the number of poles you have. If it's n, you count the number of poles you have as a function of epsilon. And that number increases if you keep decreasing epsilon.
Just some intuition for that. Is that box growing big or red shift? What is the intuition for that?
I unfortunately could not have an intuition. I really don't know. Maybe there is something to it with the effective potential, how it depends on the angular momentum. But
the size of the radial size of the box is not changing.
sure,
That's what matters for J spacing, right?
that's right.
Because this length is constant at the horizon. Maybe it's a redshift effect. Maybe it's a redshift effect. Redshift does go like square.
Well, yes.
So must be a redshift effect. So I can't understand
But
it.
this is also a redshift effect, right? You are decreasing
No,
the
that sounded to me like size of box, radial size of box.
sure.
But it somehow doesn't see the time because the mode maybe is not concentrated largely here. I'm thinking of I'm thinking that this is the time redshift. I don't understand why.
Oh, I see.
I'm not able to understand why in some clear way you get a different. But I feel that looks like a redshift. Whereas somehow for the radial thing it's not seen.
Yeah, that would be great to understand. This I don't understand at all actually. Why this is happening. In fact, this is very very curious. Anyway.
Is it just okay? You got it.
So
Effectively, the box size does depend on J because the centrifugal barrier, it keeps
the effective potential.
sort of
You're saying the box size in radial direction?
the box size in the radial.
But what's
because of the J square by R square.
But what's important for the spacing at fixed n seems to me to be the box size in the other direction. Right? Because that's what changing J is exploring. The box size in the direction of the angle.
But changing J does change the radial matrix as well.
Changing J does change it. Okay, maybe that's.
I mean, the effective potential changes, right? There's a barrier that increases and so on and so forth.
Okay,
Because the
So-
spectrum, the radial differential equation
Depends. And you take J very large, of course, it pushes down.
Yeah.
But presumably we're not in that regime yet. Right?
No.
I'm thinking that everything is sort of localized near the horizon. Is that right?
Yes.
I was thinking, Ulka, the main difference is that the redshift factor, it's this proper time versus global time. That the redshift factor, that if your mode is somehow very focused around that origin, or around a minimum, then you will get the estimate by saying size divided, 1 over distance.
I see. You mean the sphere, the size of the sphere?
Size of sphere is going to constant. But in local time, you will get like a constant scaling.
Oh, I see.
And then you translate that to global time.
I
Okay,
see what
I would then have to try to understand why the same phenomenon does not repeat. But maybe those modes are not pretty localized near. Maybe if you go to large J, Gautam's effect is making the potential barrier steeper and steeper.
Yeah.
And then localizing them very much near the small epsilon. Something like that. I don't understand.
They're far from the.
No, near to the cluster.
Um,
Near to the. I was thinking that J is not yet so large that you go very far.
okay.
But that there is a repulsion from the epsilon, something from the J, and it's giving some sharp nearby. If it's all very near, then redshift near in that region is very small. Something like that, but I don't really know.
Yeah, I don't understand it.
So there are only two wells you're saying, one on this side of the centrifugal barrier and that side of the
Yes.
centrifugal barrier.
Yes.
And is it, one of them is like log epsilon, the other is like 1 by square?
This I'm not completely sure if that's what's the right intuition to have.
So the WQV matching will answer that because the WQV wave function will be, we'll see that
I see.
the shape change.
I see. Yeah, this I would really like to understand because it happens very cleanly here, and keeps showing up in many places. And also, it's the angular momentum which gives rise to this ramp. So that's the kind of more interesting part of it. Just seen as a quantum mechanical system itself. Not anything else. Anyway, so this is the bit that I was trying to say that gets quasi-normal modes. So what you do is, of course, given this observation that you place the cutoff, sorry, take the brick wall closer and closer to the horizon, you see more and more poles come together along the real axis. And what you do is, well, you write your Green's function in terms of some, as an approximation, as an integral over a spectral function. And it so happens that, so this is the definition of the spectral function. The imaginary part of retarded correlator is this. But in this case, for these modes, etc., what you can show is that this expression, this spectral function, is actually equal to the imaginary part of the black hole Green's function, where you impose actually an ingoing boundary condition on the scalar field. So this statement is not an identity. It happens. So what do I need to do this? So I have to solve the scalar field again with the with the ingoing boundary condition at the horizon, and then I get some expression for the modes. Some poles will there'll be some poles that will be determined by certain gamma functions and ratios of them.
So this happens in the limit epsilon goes to 0.
This happens in the limit epsilon goes to 0. And this is where they exactly coincide. So that if you look at the spectral function, you can read out the black hole quasi-normal modes exactly from there. So this is precisely this picture, and also something along the line that you were saying. So there are two crucial ingredients for this to happen. Of course, one, you need a parameter to tune so that the gaps of the pole, they go very close. They condense, in other words. And you also need the residues, the features of the residues. So for example, this will not happen with any quantum mechanical system. That you will immediately see a quasi-normal mode of some. In other words, I'm trying to say that this is not this part. The second part is not a kinematic feature.
Yeah.
The first part is a kinematic feature. Okay?
It tracks the causality, right?
It tracks the causality, yes. So it knows about the black in a more slightly more non-trivial way. This I find kind of interesting, and this has a very nice parallel to this narrow resonances, so on and so forth.
It's quasi-normal mode. Physically, it's saying that something is decaying, right?
Something is decaying.
So
Yes.
here, why anything?
So here you see it's like this. So when I have gone to the continuum limit, so the poles have condensed, my spectrum is continuous. So that's like this part. Forget about this part. But in the continuous part, there can be narrow resonances. This is what weakly coupled quantum field theory tells
So it's
us.
not.
So
it would decay if you're in a wave.
yes.
You take a wave, not one mode, but a wave pattern mode. Then
This is the Bragg-Wigner propagator.
The poles there should be off the real axis, right?
These poles are of the real axis. Yes.
On the real axis.
Sorry, which one?
is?
off the
Off.
They are quasi-normal modes.
They are off of the real
Yes.
axis.
Yes.
So how can this two imaginary parts match? Here everything is manifested on the real axis.
No. So what you compute here, you see, here the spectral function depends on the residue of this Green's function, right? So the Green's function has poles on the real axis. Now you compute the residues.
Yeah.
And that you declare to be your spectral function. It's a different function altogether.
Yeah.
That function can have poles of the real axis. Right? They're not the same function. So it depends on what the residues are. It's very crucial.
I mean, if you have a complex analytic function whose poles are off of the real axis, presumably in a reflection symmetric fashion, its imaginary part on the real line is 0.
No, I think it's only the limit in which the poles are condensed to become a current.
Yes.
Then there is a jump discontinuity.
No matter what, no matter if your poles are off of the real axis, okay, and they are reflection symmetric, then the function on the real axis is real because of the reflection symmetry.
maybe he's computing like the time order.
Yes.
Time order. That thing, even in gravity, in addition to these poles, has a computer. It's because it switches between, being like retarded and advanced.
Okay. This cut is also signature of those poles.
I mean, this cut is not exactly the signature of these poles. It's just the discontinuity between retarded and advanced.
Yeah.
Okay, but it exists. He's probably going to produce that cut, and then that cut, its effect somehow will produce those guys, the higher ones. I don't know how exactly. But I think that's, I think some, okay. I'll try.
I think something like this. I mean, this is retarded. So this is not a particular time ordered correlator.
This is retarded. So then I have to.
But to be very honest with you, I have not quite understood how this happens. But what I can tell you is, technically speaking, it depends on what the residues are. Depends very crucially on what the residues are. So,
Sorry, Abhijit's question, just to ask it again, is if we're considering the retarded correlator, is there a cut in the gravity calculation on the real axis? I mean, if there isn't, then he's saying you've got a clear contradiction. Because there's a discontinuity along the real axis in your calculation and none in gravity. Right, that's his question. It's a very clear question. What is the answer about it's imitating some gravity answer. Does that gravity answer have a cut on the real axis?
I think it should.
It does have a cut.
I think it should.
Yeah. Okay. And there are many of these.
Yeah.
You would have to remember how. Yeah.
I think that should happen. Yes. Yeah.
I thought it's in the time order, but we come.
This is 1 over omega minus I gamma, and you have an integral over such things, and eventually, it does produce a cut.
But I mean, it's saying fine if your expected answer with the cut on the real axis, he can easily understand how it happened. But if you expect an answer that's analytic without any discontinuity on the real axis, then it's impossible.
Yeah.
Right?
I agree.
And I thought retarded coordinators in gravity did not have a cut on the real axis, but the time order did. I'm confused, but I'll be somewhere.
Yeah. Very good. Okay. So at least I can skip. It's not a big deal. So last, I can conclude on this. This is in some sense a bit speculative, but let me just let it, lay it out anyways. But it's at least a consistent calculation. You can do the following thing. See, I mean, there are many questions about. Again, the statements are somewhat fuzzball inspired, but again, none of what I'm doing is really fuzzball. But the point is the following: that how could you? So, if you believe in the fuzzball paradigm, how would you justify the fact that you start, for example, collapsing, let's say from the boundary, something collapses and reaches roughly the Schwarzschild radius? What stops you? Then it should collapse and form a black hole. How can you stop that? And then there's an argument that if you can generate, exponentially large number of candidate microstate geometries, maybe when it reaches the horizon scale, it tunnels into one of them, and so on and so on. So what I will do here is basically start dropping essentially a shell. There's no brick wall anywhere now. So essentially dropping a shell from the boundary of an ADS and do a certain matching, perform a matching condition to find out the full solution of. So the geometry is roughly like this, not roughly, exactly like this, where there's an F1 for the interior and for an F2 for an for an exterior. RS is the location of the shell. So you can take this ansatz, and then so basically you just let a thin shell drop from the boundary of ADS and evolve, and then you have to satisfy certain junction conditions like this Israel Lang's plane boundary condition, and then in this geometry, what I'm going to study is also a probe scalar. What does a scalar do? The scalar will also have a junction condition, and the junction condition is something that you can write in this form. So this phi1 is basically the scalar that is inside the shell. Phi2 plus is the scalar that is outside the shell, and it's normalizable. And phi2 minus is the one which I have not, I don't need it actually, the non-normalized. So there's just one comment I want to make here, is that if you look at this boundary condition or the junction condition, and you imagine that the shell has somehow reached a region which is very close to the Schwarzschild region, Schwarzschild radius, then your F2 is 0, right? Because that's what this is. This is the geometry. F2 vanishes at r equal to RH. So this is roughly equal to 0. And then the boundary condition becomes phi2 plus times del r phi1 equal to 0. Which I can interpret as a Dirichlet boundary condition outside, slightly outside the shell, and a Neumann boundary condition if you think about slightly inside, in some sense. Now I can declare that I don't want to, for example, think about the inside. Then the condition that I'm left with is actually a Dirichlet boundary condition on the field, or as phi equal to 0. This, if you wish, is a way of sort of a hand-waving way of justifying a Dirichlet quantization. So you can take this boundary condition and then quantize it, and then see what happens, and you get the features that we are discussing so far. Of course, you can do the Neumann boundary condition also. That gives you somewhat of a boring spectrum, nonetheless. But this is sort of a hand-waving way of, I guess, trying to justify how such a state or how such a configuration maybe one may be able to understand from, let's say, a collapse situation or from a boundary CFT point of view in some manner. It's not very precise, but it's still, I find it kind of intriguing that the boundary condition factorizes itself into a Dirichlet.
Sorry, I missed. How is it that it stops collapsing?
It does. This mechanism will tell me nothing about it. It will actually not stop collapse. That's exactly right. So I have to assume that something again stops it there. But all I can say is that there is a Dirichlet boundary condition that emerges when you go very close. So if there is that mechanism in place, what we are discussing is not altogether completely crazy. Good. So of course, I think I'm about to conclude. There's a lot of things that can be said. But well, let me not go too much into it because well, you can say things about type of von Neumann algebras, etc., which I really don't know. I don't understand myself very well. Jovic is an expert, and he has a lot to say about these things. But of course, this if you want to take this seriously, or somewhat, at an intriguing point of view, even there are a whole list of formidable questions which remain. For example, why should I take this seriously? Can you explain entropy with this? In some sense, so great, but that has all the usual problems with it.
You can choose epsilon so that it works.
Exactly. You have to choose epsilon plus it's the one loop determinant. Where is the gravity fluctuation and all the whole list of known questions.
Choose epsilon up to a factor, numerical factor.
Yes, that too. And anyway, so it is what it is. I don't think we can do much better than that. Maybe some incremental progress we can make, but yes, it is sort of inbuilt into the framework. Of course, and then there's a view that, well, this is not a black hole, not a fuzzball. What are you doing? You outcast from both communities, which is a reasonable fear to have. But anyway, you do what you can. Well, you make a new box, yes. Well, anyway. And one question I find it quite intriguing is that, can I actually, given this arbitrary thing, suppose we do this in the geometry and we have no ideal CFT, we should be able to do something still ad hoc to the CFTs and then write down a CFT state, which is this, right? That should be possible, at least. In fact, some progress in this direction.
Say that again, what should be possible?
So, if we are doing this, imposing this Dirichlet boundary condition in the bulk, in the infrared, we know that there is a CFT dual. So it should be possible, at least in principle, to write down a particular state which mimics this. Or what is it that we are doing to the CFT state, which would be like introducing a wall in the interior. That could be an interesting thing in itself. If you find a particularly, even if it's a very special CFT state, let's say, that could be an interesting thing.
I mean, you expect it to be a state that will survive, that will live, that will not collapse in. Maybe at one time you can expect.
Yes, even at one time. What is it? Suppose the question. It probably will not be stable.
Yeah.
I do not know how to make it stable, but
You can show me maybe states when the brain is inside the right?
Yeah, that we know. That we know.
What end of the world, man?
Yeah.
That we know very well now. So this is like taking that brain and pulling it kind of outside, and then what goes wrong with this whole thing? And anyway, so this I feel like I might be still able to say something about it because we have some progress towards that in terms of these fixed area states and so on. So this brick wall. If you look at it from a Euclidean perspective, it looks very similar to the geometric dual of the fixed area states. So it's not completely crazy. I mean, you can think that, okay, we are doing some random stuff, which it is on the outset, but still, if it's related to something, then that's more interesting. More interesting than I thought, yes. So yeah, that's also this question, and so on and so forth. And there are some follow-up calculations because we can calculate. We are calculating with this, so the system allows us to do some calculations, which is somewhat the job description, I guess. So we do it, and well, there is some notion of chaos from scattering, which you can do it because it's ultimately a quantum mechanical system and so on. It's with friends.
Sorry, the fixed state is exactly like that, right? You put some boundary condition and then you do the Euclidean path integral, that's how you make it.
Exactly.
So it allows a lot of flexibility in what the kind of state.
Yes, it's exactly. I mean, yeah.
Then the boundary condition is put on a codimension too, so.
Right. But you could, you take Euclidean black hole, Euclidean slice it, and then you have this horizon would be like a 4-dimension 2 circle, and then we can make another circle around it.
Here isn't it codimension?
Once you make it here, then it will evolve whatever.
Oh, you
Yes.
mean other points?
Yes.
Yeah. No, fixed instances are boundary conditions in the entire path integral which are imposed by codimension.
To make a state, right? Let's say on a slice.
No, I mean it's a boundary condition in the entire Euclidean path.
Oh. No, I mean you should be able to think of it as a state also, right?
Okay, you say you
thought
should
so.
be. Okay.
I thought
Fair
what
enough, fair
he said.
Roughly, I mean these things I remember only from
Yeah.
Pratik's stuff.
Yeah, so this is my knowledge about this is also a bit sketchy, but from what it looks like that there is a statement of that sort. But it's more interesting is okay, fine. So what? I mean, there has to be some more calculations, at least in my book, that it does, and in fact there might be some which we are working on. And then, as I said, there are some things of complexity and so on which I'll not talk about. This is what I was just mentioning that. Somehow I seem to be having fun with friends, and there are some friends which are more knowledgeable about these things than me. So Yanni is the guy who's thinking about these states much more seriously, and then various conversations with various people, etc. Yeah, having fun. But I really like this principle, so I'll end with this. I really do have others, and there's a particular reason why. Quantum field theory in ADS is interesting to us for many reasons, but it so happens that this is also interesting to nowadays to other people like condensed matter theorists because they can now create ADS space, Euclidean ADS space in the lab. And then there are lots of fun you can have if you want to define your quantum field theory systematically in ADS, and you want to do some lattice calculations and so on. So yes, so this is also lattice. Of course, I do not know how to calculate, but these people do. So there are some calculations we are doing. It's sort of again fun. Of course, I cannot compute entanglement entropy. I know that would be a great thing to do, but not yet. So yeah, so that's all. So thank you. Thanks a lot.
That's tomorrow?
No. And lattice, I mean, there's very little to say really. Once you formulate it, actually, no, I should take it back because this quantum link models, etc., are actually quite mathematically interesting. So you can do a lot of stuff with discretizing ADS, various stylings, and then defining quantum links and so on. But yeah, I don't know enough to say anything about that. But hopefully soon, not now.
Maybe I have more questions, but one or two pressing questions.
One question.
Yeah.
I think you explained at some point that if you try to go to the multi-particle Hilbert space, you refer QFT Hilbert space, then you use the ramp feature. Could you just say I missed why that happens?
Oh, so that happens because so this spectrum that I showed has certain correlation. Now, if you start filling up, the multi-particle sector is not interacting. So now, once I start filling it up, so they will lose all the information.
But what happens? Like the thing just decays.
The thing will be like so there I have to speculate because the multi-particle sector is something we cannot numerically compute. It's widely fluctuating and so on. But I would guess that it would be like a harmonic.
Oh, it's harmonic. It's
completely featureless because it's a free theory. After all, so in a sense, it's reassuring that you actually get the boring sort of expected answer you get from the multi-particle sector because it's a free theory.
No, but with the black hole, it should also fall. It should also fall in.
Yes.
And it's free. So
true.
Some in between behavior.
Yeah, probably. But yes, this is something we could not calculate and kind of there's not much point in calculating. You know what it is.
Well,
I mean, yeah, given a spectrum, unless you tell me that I cannot put another particle here, I am going to do that and then it's destroyed. There's no level potential.
So what? I mean, multi-particle, you don't have freedom, right? Once you have single particle, just to exponential. Right?
Yes, exactly. So what I'm saying is that given a particular, so level repulsion comes from the fact that no two energy levels will come arbitrarily close to each other. But given any spectrum, if you allow me to put multiple particle into it, then the resulting energy spectrum will have no information that there was any repulsion between them.
Because this guy's
Yes, so unless you turn on interaction. Interaction makes it, that's the challenging part of motions.
If you want a shell collapse and not form a black hole, you can do that by remaining in below the Chopin limit. But of course, it will prevent that in the first go.
Yes.
Then it will, go to the boundary and then come back again and so on and so forth. So eventually it will. But for some time,
Sometimes
you can have a non.
I see. Yeah, that is true.
This kind of stuff will have some meaning in the CFD.
Sure.
Yes. Yeah. So you can tune your time scales and so on. That
So they come together and then they go
they
out.
come together and then they pass by.
Pass by. Yes.
Yeah. So it's just not dense enough to form a black hole. But then it comes back because it's in flat space, that's it.
Right.
It just doesn't form a black hole. So there is a genuine phase transition between less dense and more dense. One in one shot. But in ADS, you're not so lucky. There are many Chopin transitions at the first pass, second pass, third pass, and so on. So eventually it forms black hole. But for some time you have some respite that you have not formed a black hole.
Also in areas you have configurations that form black hole after the entrance.
Yeah. So if you are less dense than forming a black hole in the first pass, you might form a black hole in the second pass, and so on.
So that in CFT is some oscillatory stuff.
Yeah, you can actually in some SYK context, I know how to do this, but
Interesting.
Further questions, let's take them.